So all the way on top, blah, 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 Pybrain, Python intro, and then a bunch of files and folders, and then a bit of explanation below that, about what we'll be doing today, and also a little schedule of when we'll be doing what. It's a very rough schedule. There'll likely be some independent work during most of the things that are flagged as presentation, because it's much easier to do independent work than to listen to me going on about whatever crap that I might be going on at any moment. So we'll start with the very basics, then we'll work up through Python. The very basics being literally the very basics. There's no prior knowledge required for any of this. The only thing that will be requiring is some very basic computer literacy. So for those of you with a Google account, you can scroll all the way down, and there's this thing called Google Collaboratory, and each of the links, there we go, each of the links here links to a particular Jupyter notebook. So the top one is the one that will start with this first hour. So you can hit that, click on it, and it'll take you to the Google Colab page, which looks like this. Now there's a little trick, and this is where you really need to have a Google account. Once you're signed in, you can start actually running these things, because they don't do it if you're not logged into a Google account. The nice thing about this is that you can actually copy it to your drive, your Google Drive, and then anything you change on the actual notebook will actually also be stored to your local drive, and it's easier then to get it offline afterwards. So if you do have a Google account, please start using this. If you don't have a Google account, not to worry. What we can do is use a slightly different tool, which is my binder. So back on the GitHub side, if you didn't click that first one because you don't have a Google account, launch this repository in my binder. It's the link that you're now looking for. And if you do that, it'll get you in this place. Now what it really gets you is it'll open my binder in the background, and it'll show you a little loop-de-loop, and it can take a little while. Essentially, this is something that usually takes a while to start up, because what it's doing in the background is creating this personal environment for you where it just installs all the necessary packages and has a local version of Python. So essentially, it's doing stuff in the background. It'll take a while. That's just what it is. Excellent. Let's see if I can keep an eye on the chat whilst we're doing this. All right. Cool. So throughout this entire thing, there's two things you can do to get my attention. The first is trying to ask a question in the chat, and the second, which is much more likely to work, is to shout. So if you do feel like you have any questions, do ask. We've just recently started doing undergrad teaching again, and this feels very similar to that, because you're just talking into a void, and very often it doesn't really feel like anyone is paying any attention back. So I'll just keep going. Please do interrupt me if there's anything that you want to have clarified. Okay, so assuming that everyone in the background has now found their way to either Google Collaboratory or my binder, depending on whether you do or don't have a Google account, or one other option is that if you do have Python running locally, you can, on the GitHub environment, just hit the first folder and then hit the first Jupyter notebook. You can recognize those notebooks by the extension IPYNB, and it'll load in very much the same way. Sometimes this doesn't really load, and then you click reload, and then it does. Not sure why that is. Excellent. All right, so assuming that everyone is now on either Google Colab or the binder or their own their own GitHub environment that they'll be running on their own local Python installation, we're going to go to the first notebook. Just to clarify, this is a bunch of folders rendered in a slightly weird online way. We'll go through them one at a time. So usually there'll be like one folder per hour. And the first one that we're going to look at is the Jupyter variables and functions. Once you click on the folder, there's usually a notebook icon. There's always actually a notebook icon. You can also recognize the file by the ending again in IPYNB, and that's the thing you want to click on. Because if you do that, what happens is that it loads the entire worksheet in a browser. And these worksheets are pretty cool. They're essentially a mixture of text, which you can read like any normal person, and also code, which your computer can also read. So essentially what you can do now is go through all of this, and it's a really, it's basically a textbook, but it has some interactive elements that you can use to run some code in. A lot of the code will be pre-prepared, and will be really easy to kind of just click, hit, run, see, I guess it works. One thing I really strongly recommend is to just actually read the code and maybe make some changes if you see fit. Further down the line in plotting, for example, just go nuts on whatever kind of colors you want to add, or different types of plotting markers. It'll be a bit less exciting to vary on the statistical tests, but usually the morning and afternoon sessions end with a bunch of assignments where you're supposed to do your own coding on the basis of what you've done before. So it's really quite useful to have actually done some coding before that. All right, so where we're going through these notebooks, essentially, reading through, I'll let you do in a second. What I just want to show is that these are the interactive elements. If you hover over them, they become nice and active. And one thing in Google Collaboratory, you'll see this run button that appears over the actual code. Only thing you have to do is just click on that run button. In Binder, what you can do is hit the run button all the way on top. And then what happens is that the code in your actual window is actually being run in the background. Now, this is just a single function that you can use. You can also use this to do other things like assign variables. And then obviously we actually need to show the variable. And you can do all sorts of other things in here as well. For now, we've prepared 3 different packages in the background: numerical Python, scientific Python, and a plotting library called matplotlib. And all of that is already pre-prepared, so you don't have to do anything for those. It's probably useful to know that Python itself is a language that consists not just in a vacuum. It has other packages as well that some people make for it, and you can use as kind of add-ons to your Python. So Numpy, SciPy, and Matplotlib, the 3 libraries I just mentioned, are those external packages that you can. So now would be a great time to start all the way at the top of the Binder thing and just run through it in your own tempo. What it will do is it'll guide you through all of the variable types and through the basics of functions, which is what we'll be doing for the first hour today. Just run through it. If you hit any obstacles, be sure to share in the environment here, because that's where essentially we're going to do all of our problem solving, troubleshooting, answering of questions, whatever you want to call it. So have fun on Binder, Google Colab, or in your own local Python environment. And if you run into any issues, give me a shout here or in the chat. Just for everyone following along with their own Python distribution next to their browser, if you're following along on Python, if you're following along on GitHub, that's exactly the place where you want to be, but also GitHub doesn't offer that kind of in-browser running virtual environment, essentially. So if you are trying to follow the stuff in your own Python distribution, the easiest thing to do is just copy the code over from the GitHub repository into your own Python distribution. Provided you installed Anaconda or installed the external packages that we just talked about, you should be all right for, you're right for everything in the. So there's a great question from Celine, who's asking whether there's any difference between using single or double quotes or even those triple quote marks. There isn't really. Python will parse them in the same way. The one thing you can imagine is that if you wanted to use single quotes within your string, it's easier to use double quotes to bookend the string, because then it doesn't get picked up as an end thing. I'll post an example in the chat. There we go. So for that string, for example, when there's a single already in there, You obviously don't want to use those to bookend the side of the string, because you'll essentially confuse Python into thinking a string is already ended when there's still an ongoing thing. So that's really the only point where it starts making a difference whether using single or double quotes. Other than that, Python itself will pick it up as single or double, or even when you use those triple quotes. So nope, not really a difference. Great question. So Frank asked whether with for loops is there a way to state the end of the loop, or does it look at the indentation / line break? So in other languages, if you start a for loop, normally at some point you say end, and then you know that that's the end to the for loop. Or you use curly brackets to define the block of code that needs to be run by the for loop, but nothing else. So in Python, the indentation is actually part of the code. So the moment that you re-indent to the same level as the for loop, that's where the for loop code ends. And that's how Python knows. So yes, the indentation is how you signify the ending. It can be a bit disorienting at first if you're used to different programming languages. But I actually find it really helpful, because in all other programming languages, you end up writing code like this anyway with indented blocks, so that it actually is readable. And in Python kind of forces you to do that. So indentation, that's how you end it. So if your binder stops working, the best thing is to just quit and close it and restart it. Usually it'll kick you out after a certain time. So it's probably just timed out. If it doesn't work, if you refresh your browser, just re-click the link on GitHub and you should be able to access it again. All right, where you should end up is here. And I'll briefly go through functions because they're quite important. Classes are too, but we'll get to that in a bit. So Python is a bit funny because it actually, we'll come to that in a bit. First, just do the functions. So as Frank just asked earlier, there is this weird thing in Python where indentation actually is part of the code. So if you look at this toy function name here, for example, this toy function definition, there are a few things that set it apart from perhaps other types of function definitions. So the first one is that you don't actually define any of the output in the actual name. So when you want to define a function, you use the def keyword, and then you write whatever your function name should be. This is up to you. The only point is that you shouldn't start it with a number, and also there shouldn't be any spaces in there. And I would also recommend not using hyphens, because they are also a functional thing. So essentially, there are a few limitations, but within those limitations, this can be anything you can be. And then between brackets, you provide whatever the input should be. Now, these inputs, they can be one of two things. They can be an argument, and an argument is just the variable name written out. And what you're actually doing in the background is creating this variable name within the function. So if you define it within this first line, you can actually use it a bit later in the line. So for example, here, we do something with that input A, and we also do something with that input B. So if they're in the function definition, they are locally defined within this function. So you don't have to say input A is outside of the function whenever you want to use it. You just pass it to the function, and it's usable. Note that the the colon on the end there ends the function definition start bit, and then after that comes the actual code. So that's this part here. We'll come to this part here in a second. So in this part here, you have the arguments that you created in your definition, and you can use those in whatever way you see fit. So in this case, probably the expected input is two numbers. You add one to the other, and then that's your. So in this case, we just create a new variable here. And the kind of sneaky thing about functions is that whatever happens within the function stays within the function. It's a bit like Las Vegas. So the idea is that this here is, this variable here is only created within this space. So if I were to, outside of this space, call the variable output or try to access the variable output, it shouldn't exist, which is useful because it kind of makes this a really nice self-constrained thing, a bit of functionality. It's also therefore important that you do take out of the function anything that you don't want, that you want to use outside of your function definition. So essentially what you're wanting to do is return those things back into the space that you're working in outside of the function definition. So we define our function name here, but what the returns are only defined when you call the return statement. Returns are the outputs to a function. So in this case, we call that variable output, but you could call it something else as well. And in fact, let's just start with a nice little dummy. So I have A and I define that as a number. I have B and I define it as a number 2. And then I want to define a function, and I want to define a, let's say a sum function, just that takes 2 inputs and adds them together. So the function is plus. I take my first input, and we can give that any name that we want. So we can call this X, and we can call the other one Y. And then we say our output, which we can also call anything we want. So we can call this the sum total is X plus Y. And then after that, we can say plus A comma B. And it should allow us to use this function definition to do that. Now, if we run this, there's no output at all, because we haven't actually done anything with the outputs defining in here. So essentially what we've now just done is within the local function, something happened, and we can't have access outside of that. So this is what I was saying before. If we're trying to go for that sum total now, we don't actually have our access to it, because that sum total is not defined outside of that function definition. And this is why you have your return statement. There we go. So if we run this, we still don't have the actual outcome because it just returns it, but we're not actually using the return when we call this function here. So instead, what we're going to do is say outcome equals whatever that is. There we go. So now essentially what we're doing, we've created our function definition. It takes 2 inputs, it sums those inputs together, and then it returns the outcome of that. The way that we're treating that outside of the function definition is we're popping in our newly defined function 2 inputs, A and B. So those will translate into the variables X and Y locally to the function. And then we're also creating the variable outcome, and we're assigning whatever comes out of the function to that variable. So now if we run this, whoop, we neatly get the sum of those 2 together in the outcome variable. Now, that in a nutshell is functions. That worksheet that I just popped in the chat is basically a larger explainer on this, and it has a few assignments in there as well, where you can practice with defining your own functions. So happy working on there, and if you do run into any issues, please do let us know in here so that we can address those centrally, because it might help other people who run into similar issues as well. Have fun. All right. I'm just going to go over the functions so that we can see them all together, how they actually work. Considering nobody's asked questions, I presume that people found it easy enough to do, but let's just do it anyway. So over here we have the function for the sum, and we are passing a list to that, and then checking whether the type was actually a list or a tuple. And if it wasn't, then we're going to say return none, because we can't actually sum this. It's a really useful thing to do in general life, where you do this type checking before you're actually doing anything to the input, because you're writing this function with in mind what's supposed to go in there, but really what people can actually pass to that function is essentially everything. So if somebody else will use your code further down the line, or more likely, if you will use your code further down the line, like in 2 weeks from now, and you will have forgotten everything you've written, then it's really useful to have these kind of. Normally, simply returning none might not actually be the best approach. Instead, what you could also consider is throwing like a formal error, but we can go into that if there's a bit of time that's kind of beyond the very basics. So for now, we were just going to try and loop through the list of numbers that we have, and then we were going to see if we can add those to a sum total. So we're starting with 0. We could also start with 0.0 if you wanted to explicitly return a float. which is sometimes useful, sometimes not, depending on what is passed. The nice thing about Python is that if there's any floats in the numerical list, and if you use the plus operator to add them together, they'll implicitly be copied anyway. Be converted anyway. So you could also just choose to start with an integer, because then if the list contains only integers, your sum will stay in the same type, depending on what kind of data you're working with that might or might not be useful. Right, so we're for looping. So there's one thing you could do is say for value in num list, for example, s is s plus the current value. So with this one, we're looping through all of the numbers in our list. And with this one, we're adding to our current sum. We're saying the current sum is whatever the previous sum was plus the new value. One kind of shorter way of writing this is to use the plus equals operator, which is essentially the same as saying s is s plus the value. It's just shorter writing, and it can look a bit cooler, I guess. And then the only thing that's left is to return the actual sum, so that's available outside of the function definition. So if we run this and then test it on our list, that works really nicely. Oh, right. So the second is to compute an average. And secretly, that's actually really similar to what we've done before. So I'm going to copy bits of the code over because I'm a very lazy programmer. So this was for the sum, boom, overwriting that. And then what we wanted to do now is divide the sum that we found by the number of elements in our list. There was a function to get the number of elements. So let's call it n is the length of the list. And then the only thing that's left to do is to return the average, which is the sum divided by the number of items in the list. So what we can do is say return s divided by n, and then that should return the end result of that operation. If you wanted to do it slightly more neatly, you can say compute the average, which should be s divided by n. So we can say, and then just return. Doesn't really matter which way you choose. One can be a bit quicker to write. The other can be slightly better understood when reading over it. Again, some of these things are purely based on your own personal preferences, and there's a benefit to having very readable code, even though the actual code itself is not as clean or not as as minimal as it could be, because realistically, the majority of time that you lose on this is not by actually typing the code, but is by having to reinterpret the code once you're actually reading it, or it's for other people to have to interpret your code. So there is a really big advantage to writing readable stuff, human readable stuff, over computer elegant stuff. All right, so just checking whether that works. Yeah, our average is 5 here and average 3 here, so that's absolutely correct. All right. This last one, penultimate one, sorry, is for, is it penultimate? Yeah, it's penultimate one. It's for computing a grayscale value. This is a luma value for those of you who've done vision science or have had to calibrate a monitor at any given point, be familiar concept. The idea is that we're not equally sensitive to red, green, and blue. And therefore, if you want to create a grayscale image that is kind of equal to intensity to how we perceive the same, the color image that was the original, you can't just average the red, green, and blue values of your color image to produce the intensities. You actually have to kind of make sure that the intensities are weighted in such a way that they kind of match the human visual system. We're going to use this conversion for that. It's one of many conversions you can use, but it's a quite well-used one, and specifically useful if your gamma has 1, because then this reduces to RGB. All right, so the first thing we do is we, again, use that function definition, and we're assuming that people pass red, green, and blue values as a separate integer or float. Doesn't really matter. The most likely data type for this is going to be a unsigned integer in a space of 0 to 255, but it could also be 0 to 1 or even -1 to 1. Different libraries use different ways of defining color. Can be a bit annoying, but at the same time, if we're a bit agnostic about what those values are, we can actually treat it quite nicely. Although actually, I think I said, yeah, we're supposed to round to the nearest integer value. Okay, never mind. We'll just assume that everything that comes in is between 0 and 255. So first is to compute the luma. Let's call that y, and it's basically the equation that we saw on top there. So it's 0.299 times red plus 0.587 times green plus 0.114 times blue. And then we have the y value. Now, one immediate downside you'll spot is that this is an implicit float conversion. So our y value will not definitely be a floating point value. And it can also be a not actually well-rounded value either. So the first thing we want to do now is to round the actual value. So we're going to say y is round y, comma, n digits is 0, because we don't want any things after the decimal separator. We can then also explicitly say y is int y to make sure that it's actually an integer value, and then we can return y, and that should give us the gray values in the end. So we can test that over here, see if it actually works, and it does. So this hot pink value converts to a 158 brightness value, and 0, 127, and 255 for black and demi-gray and white respectively. Any questions at this point? Excellent. Excellent. So standard deviations. Basically the same as an average, but then we're actually averaging the distance to an average rather than the actual value. So one thing we need is the actual average. So I guess the first thing to do is, if you have this input for a number of lists, is to compute the average. Average. And we just made a function for that. So that's super useful. So one thing we can do is we can go back to the function average. There we go. So that's our mean. It's really useful to do that so that you don't have to actually copy the rest of the code for that out of the previous function definition into the current. This is actually a strength of where it becomes super useful to define these functions if you're doing your own scripting, because oftentimes you'll do the same thing over and over and over again. And it can be really useful to encapsulate that same thing in a function so that you can then call the function whenever you have to do it, and you don't have to copy paste your code all throughout your script. So extremely useful to just have this kind of back pocket of functions that do specific things that you frequently do to your data. All right, now that we have the average, we need to start actually computing the standard deviation. I'm just going to follow the stuff that we have here outlined, so the steps that we have outlined here. So we're starting with a sum of 0. So let's say s is 0, there we go. And then we're going to look through all of the elements in the list. And for each of those, we're going to compute the difference between a number and the average of all the numbers. So that's the average we computed there, and then square the difference. So for all numbers for value list. There we go, that's the loop. And then we're going to compute the square. Right, so this difference is pretty easy. That's just the value minus the average. Squaring, we can use the double asterisk for that, and a 2. So that's basically exponentiation by 2, or a square. And this is what we wanted to add to our reflexive hitting Command S. So essentially, for every value, we're adding to the current total whatever the difference of that value and the mean is, and the square of that specific. So the square difference, essentially. After that, what we want to do is, there we go, divide the somewhere differences by the number of values. Excellent. So we say s divided by length num list. Excellent. And we want to also take the square root of that. And now this is where we need the math function, math.square root. But we haven't imported that yet. So what we need to do first is say import math, and then we can actually use those lovely math functions that are in here. And then the only thing left to do is say return the standard deviation that we just computed. Run that. In the meantime, my cat just walked in and usually expects a treat if he does. And then now we can test whether our st function actually works. And pop, we have 15.15, which is right because I created this data to be roughly average around 100 and having a standard deviation of about 50. So voila, that's the answers to the questions here. Stop my screen sharing. We have a break now up until 1 p.m. And at that point, we'll continue with Numpy and loading data from text files. Also, normally I'd be walking around the room, just kind of casually checking in on people's screens to see where people are at, which is obviously very impossible now. So if you could send me a private message on the Zoom meeting, on the chat, if you're done, or a public message if you're proud of the fact that you're done super quickly, that'd be great as well. All right. I appreciate that not everyone is done yet. In fact, most of you don't seem to be done. But there's a few things I wanted to highlight before the official work yourself time is starting. And those things are the following. So if you're following on the screen, there's a few potential weirdnesses here there's a few weirdnesses here, and essentially one of those is this kind of with statement. And opening files in Python can be done in various ways. The most straightforward basic way is to use this open function. So one thing you could do, which might map on better to what you're currently thinking about Python, is saying, well, let's say my file is open, and then whatever your file name is, and then the read flag. Using the read flag, super important. If you were to use a write, for example, you would be overwriting the entire file, so probably not the best to do. So use the read flag, and then do stuff to my file, for example, read lines or whatever, and save that. And then you would say my file.close. Now, this is a very sensible way of doing it. The first one is quite clear. You open a new file, and that open file is then this my file instance. After that, you can use some of the methods that come with that instance, like reading its content or like closing it. The downside of this is if anything happens between you opening the file and closing it again, it kind of leaves the file in a mess. So your operating system might deal with this very elegantly, or it might not, but it's not really good coding practice to allow for a file to potentially stay open like that. So instead, what you can do is use this with statement. So essentially doing almost the same thing here. We're using the open function to create this open file. In this case, we're calling it open file instead of my file, but that doesn't really matter. You could name it whatever you want to. But and then after we open it, we use its own method to read the content. But the benefit of using this with statement is that after you've finished with it, it already closes the file automatically. So the moment you kind of go from this indented code to the non-indented code again, the file is closed automatically. In addition, if something were to happen during the file being open, say an error pops up, the file is also closed automatically. So this is a really elegant way of making sure that files are properly handled and closed, even if unexpected errors occur. So that's why we're using this particular format of doing things. So that's the first weirdness. The other weirdness is once you've actually loaded the file, we were doing slightly odd things to it. For example, this \n character might be slightly strange. Now, in all of your files, whenever you open them in Word or in even a text editor, there's a few characters in there that aren't meant for your eyes, or that are meant for your eyes but are rendered in slightly different ways. So this new line is one of them, and it's essentially the character you introduce when you hit enter. So it fits on the back of all of the lines that you might read from a file. And in order to get it off again, because normally you're not really interested in this, you'll have to actively replace it. In this case, we're replacing it by nothing, which means that we're actually just removing it altogether. And then the second thing that's a bit weird, perhaps, is this splitting by. So this just finds all of the occurrences of a comma in your string, because the line that we just read is really just that, the string representation. So it finds all of the commas in your string, and it cuts the string apart into a list with all of the bits between those commas that occurred in your string. The commas themselves are then discarded, so you don't see those back in your resulting list. Great. So that's the one kind of weirdness that you have when you deal with very basic Python functions to do data reading. The other weirdness is perhaps you have when you're loading loading text files using NumPy's functions. So this was perhaps the most straightforward way of doing it. When you have a header in your file, the first line, first row, just giving you the variable names, then usually that will be a bunch of strings, because those are usually text to indicate to whoever is using that file what is actually in that file and what each column means. It can be super useful, but it also means that whenever you load that data in, you now have a problem where you have numbers mixed in with string values. And as I said before, NumPy arrays can only take one type of values. So if you're loading one of those file types, you can't just load them all as a numerical value, because the first row is always a non-numerical value. So this was one way of getting around that. You're just skipping the first row and thereby just not bother with the header. And the way you solved it here was by reading the header from a different file. The other option here is to load the entire file, but then load it as a string data type. And then somewhat complicated things happened. And the somewhat complicated things are specifically, we used a dictionary to create those things. And a dictionary is essentially much like a list or tuple, in that it is just a collection of variables. But unlike a list, where a list had very strict keys to indices to get a file back, to get a value back from in the list. So the first value was the list and then 0, and the second value was the list and then 1, and so on. A dictionary allows you to set keys that you want. So instead of a 0 for the first one and a 1 for the second value and so on, you can use a, or dog, or it's raining outside, or basically whatever you can think of, you could use as a potential index. And that's what we're doing here. So every single time that you see this my data being referenced, or at least the important one is this one here, where we add a particular variable name. So the variable name will come into a second. It's parsed from the actual file. But what this particular thing, bit of code does is essentially saying, in this dictionary, create a new entry under the key variable name. And that particular key you can now use to refer back to your data, which is why this later down the line works again. So just to play around with this a bit, if you create a dictionary, say, let's use the same notation because it's probably less clear otherwise. Now, if I use a dictionary like this, and then I run my thing, I just have an empty dictionary. And then boom, we just have an empty thing back, right? Now, one thing we can do is say, I'm assigning to this dictionary A, and whatever, just let's say it's a random value. And now I have in my dictionary that key and that value. I can add other things as well. 15, and I can even mix in numbers if I wanted to. There we go. So the dictionary contains all of those values, and a different way of getting at them is by indexing in the same way as you would normally do a list, so with those square bracket notations, and say 0, and that gets you back the value under D0, but you can also say A, and that would get you back the value under A. So that's what a dictionary is, and I can't quite remember whether I put it in the overview at the start. I probably should have, considering we're using them later on, but this is just a wee bit of either repetition or new information, but that's how dictionaries work, and that's what we're creating here. This for loop here is just combining things that you already know. The range function creates one of those ranges of different values from 0 to whatever the values you put in. And you put in shape 1, which happens to be the number of columns in the data file. And then for each of those columns, what we do is we take the first value, so value at 0.0 in whatever column we're currently at. And we also take all of the other values in a slightly different variable. And that is, from the first colon means all the way to the end. And I is again the column number. So first value, and then the values from the second position all the way down to the end. So those are essentially the variable name, the string, and all of the values, which in this case are numerical values, but we don't necessarily know that because, ideally you'd be loading files as they come in, and you don't necessarily always know what the column is that you're doing, or at least that you're dealing with. So one way of dealing with that is trying this approach beyond here. So this is essentially a combination of two things. The first one, what you could do is just blanketly try to cast the values that are currently in a string format as a float. And if this works, then it's great. If it doesn't work, then it's likely that your values are supposed to be strings. Perhaps they're actual names or email addresses or whatever. And those are supposed to stay in a string format. So there's no use in casting them as floats. Whereas these could be reaction times or onset times of a particular screen. And those could potentially be floats. So those will automatically be casted. This try except is essentially, if this thing results in an error, try this other thing instead. So that's one way of doing it. And another way of doing it is explicitly putting variable names that you might know shouldn't necessarily be casted. For example, participant number was something that we didn't really want to turn into a float because it was just an arbitrary participant number and not something that we wanted to do any computations with. So in this case, we opted to not cast those. So we explicitly put those variables in a list and then said, well, if the variable name is not in that particular list, then we want to do that casting as a float. All right. So after just resetting those values as a float, we can then store them in a dictionary. So again, under the variable name that we parsed as the first part of our column, we store all of the other values in the column from the first position all the way to the bottom. And that's what that for loop does. Oh, right. I figured that was worth it to highlight because it was a bit of a black box when that popped up in the sheet, perhaps. For now, I'd recommend starting on the second sheet and or taking a bit of a break. The second sheet being actually the fourth read, not the second. Let me pull up the link and post that in the chat again. This one goes into plotting primarily, data visualization. And one thing it does is also provide some assignments to do that kind of combines the Numpy aspect and the matplotlib aspect. And those you can work on in the next hour and a half. Be sure to take a little break as well. and I'll check in again in about half an hour at about 2:30. I'll post the next stuff in the chat. It's a screen full of names, isn't it? Oh, you're all green. Oh no. So for those who are already at the DIY color plotting, the third dimension in there relates to the color. So that's where you think back to the RGB from before. And RGB, of course, are 3 values. And from the questions I'm getting, it seems that quite a few people are making their way through the quite far into the plotting, the 4th worksheet for today. If you are done, could you again send me a message on the chat, or just let me know in the thing here by shouting, "Oh, I'm done! Yay!" Bro, just go one of those messages. If enough people are done, we'll go through the assignments like collectively so that we can see how they work essentially. But officially, there are still 45 minutes in the whole session, so take your time if you're not there yet. I think in about 15 minutes we might start and have a look at them collectively, provided enough people actually make it towards there. Right, can I see some thumbs up for people who are done with the final sheet? Excellent, that's quite a few. Nice. There's about half an hour in a formal session left, and also the nice thing about this online format is that all of the sheets will stay online, and for as long as the websites are up, you should be able to use them. So with that in mind, I'm going to take you guys through the assignments and what the potential answers could be. And then if you haven't finished them yet, you can always return to them later, either after I'm done speaking or after the session somewhere. So I'll pop open Firefox on a share. There we go. Make sure you can see the chat in the background. Go. All right, excellent. So assignments, the visual noise one. We actually, I made this really easy. Somebody pointed out that I forgot to actually delete the answer to how to make 2-dimensional noise. Whoops. So that was an easy one. Bottom line is you create a figure using the figure function, and then we created axes. And one of the weird things in axes was this little thing here, where you provide this rectangle, and essentially what it is the left and the bottom coordinate. So where within the figure would you like your inset essentially to start? And in this case, we started at 0 and 0, which is all the way in the bottom left corner. And then the next two were the width and the height. So one is 100% of the figure, and the other one is 100% of the height of the figure. In a normal graph, you wouldn't normally do that, because what then falls outside is the axes. So you wouldn't be able to see the x-axis and the ticks and the writing on that, nor the y-axis and the ticks and the writing. But because this is supposed to be like a full-on graph, we do want to show both of those. We kind of ignore those. So instead, we just put the full space to use. And the next thing up was to create 2-dimensional noise. And as the answer already showed, you can use NumPy's random.rand function to do that. Rand without the n on the end, because we're creating uniform noise rather than normally distributed noise. And we can say, let's say 200 by 300. This will be values between 0 and 1. We can pass that to the imshow function, and the imshow function is quite useful. It essentially just takes a numerical representation of an image essentially, and it uses that to create an image. You can set certain color maps, and in this case, it's nice to make a gray, which is a black and white color map. And then if you run that. Oh dear, must have not run my top of the thing statement. There we go, let's fix that. And now the representation is real nice in black and white static, as you might see on a very old television. Two things to note here. The thing is that here the height and the width are in a different kind of orientation you normally expect. Sometimes that is the case in images in Python, so specifically for matplotlib's ipshow, but you also have the same thing occurring in things like OpenCV frequently does it as well. So if you're at some point down the line trying to do, let's say, image analysis over long sets of images or videos, then OpenCV is Open Computer Vision is a good tool to use there, and they have the same kind of height, width, and then depth makeup, which might not be what you're used to, because I think a much more common thing is the width versus the height, which is also the case in the rectangle here. Anyway, this is great. Saving the figure was fig.savefig, and then whatever name you want to give it. So let's say gray noise.p. Whether this works and where this works depends on where you're running this. Excellent. There's a few other nice little quirks that you can explore here. For example, color maps doesn't need to be gray. There's other color maps that you can use as well, and that make it slightly more exciting. Viridis, for example, is a perceptually uniform map that goes from blue to yellow. And these are things that you could potentially use in actual plotting as well, where those perceptually uniform maps can be really nice. There's another one, I think it's called Magma, that's also perceptually uniform, but goes from purple to yellow, also quite nice. All right, next up, colorful noise. So this one you were completely on your own, but you could use quite a lot of the things from the previous assignment as well. So first you create a figure using the very same pyplotl figure. We add x's in very much the same way. And there we go. But now the three-dimensional noise. This is one that I got a few questions on. So one thing that you could potentially do is write random.rand and then say 200 by 300 and then by whatever other value, let's say 100. I've seen that pop by once. The issue is we wanted to create noise that has color without setting a color map this time. So we also previously learned that the way that colors are usually represented is as an RGB value. So what we have here is the height, the width, and then the color depth, which is 3 because it's R, G, and B. So we should set that to 3. And then we can plot that again. So axle intro noise. And then running that gives you a lovely mass of pixels in all sorts of different colors. So that was the trick there. There's not that much more to it. I had the big again, which we missed out. So color. One really nice thing, by the way, from the save fig is that it automatically notices and recognizes the file format that you put in. So if you make this into a PNG, it'll obviously turn it into a PNG, but you can also make it into a JPEG or a TIFF. TIFFs are lossless and tend to be huge ass files if you make the figure quite large. So be careful when you do that, because at a certain DPI you can have suddenly like 300 MB worth of pictures suddenly in there. But it can also be super useful if you're submitting to journals that want really high quality and really specific file formats for line drawings or for graphs. Another thing that's super useful is, as I said, the JPEG one automatically converts. And there's a few other file formats in here that you could potentially use as well. One of them, for example, is SVG, which is a vector drawing. And in this case, it's then saved in vector format, which works nicely if you then import it in something like Inkscape, for example, because vector images are drawn in such a way that the directions that are stored are actually the drawing directions, so you can scale them infinitely, essentially. So this can be a particularly useful way of saving as well. Cool. And then the final one, was to load data. Now, I'm referring to the file name here again, which is that format that we set at the start of the notebook. So that, again, depended on whether you are running from Colab or not. In this case, I set the path to whatever is on my my Google Drive, and then run that and use that again further down the line. So that's what I'm loading here. And now we have X, Y, and Z, and we're trying to plot that in different ways. So I guess the most straightforward way to complete the assignment is to just go back a bit and borrow, or outright steal, I guess, the code that we have here. So one thing that was important for plotting here was setting a few positions. Just going to blatantly copy that here, because it's nice to have a violent plot. Now, those positions were specifically positions on the x-axis, and now we're a bit confused, at least in a slightly confusing space, because I've named these things x, y, and z. So I'm going to undo that confusion and name them A, B, and C, so that we're not confused with the different X and Y axes, and also X, Y, and Z groups that aren't actually related to each other at all. So I'm going to name the groups A, B, and C, and then the positions are the positions on the x-axis for each of those different groups. Now these can be relatively arbitrary, and I think I should put 2.5. There we go. These can be relatively arbitrary because it really depends on how wide you draw your violin plots or your bar plots or your whatevers. And the idea is essentially that we can set these to whatever we like, but make sure that you think about roughly where what relative distance you would like them to be. So you have those positions, and then we're going to draw our violin plot. So again, borrowing from before, I have my little plot here, but let's set this to an actual figure that we create. So let's start off by saying here and using, there's actually a really neat way of just creating a figure with subplots already, subaxes already. And that is if you say x by plot subplots. And now this is super useful because you can essentially create one figure with a bunch of different subaxes when you go, but it can also be useful if we're only creating one subplot, which we're doing here. So you can set the n rows and the n cols, which is the number of rows and the number of columns that you'll have in your subplots. So for example, if I set n rows to 2, and n cols to 3, I would have 3 different subplots, columns for subplots and 2 rows, which would give me 6 subplots altogether, and all of those would be in this axis thing. However, in this case, I'm only creating 1, so I just want the 1. I can also directly pass things like the fig size, so I could set it to be, I don't know, maybe 10 inches wide and only 6 high, so that it's slightly wider than the usual default format. And I could set my the number of pixels per inch to, let's say, 300, so that it's a bit higher than normal, so that the resolution is a bit better than normal. And then I can use this axis straight away without having to fumble around with the create axis and whatever. Can be really useful to do this automatically, because now I don't have to sub-specify, what the rect is for each of the axes. All right, so I can use this axis now to create this violin plot. My groups are now A, B, and C, and my positions are predefined. Those are the 0.5, 1.5, and 2.5. And I'm just going to create a plot. So just the kernel density estimate, they call that. So that no means in there, no medians in there, and also I'm just ignoring the extrema. Excellent. Just to show you what that looks like without any further. Boop. Also checking where it actually works. Yeah, there we go. All right, so now we have 3 blue violin plots without anything in there, but the assignment was to make them different colors. So I'm going to make another little list that I'm going to call use for the colors. So colors. Let's call that call. Okay. Now, colors are defined in different ways. So one thing you can do is say, I want to use just red, or even just R, because R is also something that Numpy recognizes, Matplotlib recognizes as red. A slightly more exciting thing to do is use these hex values. Those are hexadecimal values. They have 3 codes in them. So for example, FF is the maximum, 00 would be the lowest value. So I could set FF0000, which means full blast on red, and then nothing on green, and then nothing on blue. So the first 2 values are the red values, the second 2 values are the blue values, green values, and the last 2 values are blue values. I could also set this to different values. Let's make the first one red, and then make the second one FF, so full on red, 69, so not that high on green, B4, so again, slightly higher on blue. Doesn't really matter if this is capitalized or lowercase, but this happens to be the hex code for hot pink. Great color, would strongly recommend people use it. And then the final one, maybe another reddish shade, but maybe a bit lighter this time. So if I make the values ever so slightly higher, there we go. Excellent. So now I have 3 colors. And that also means that I can now start using that same logic that I've used before to loop through the violin plot. So when you create a violin plot, it creates this dictionary, and in the dictionary there is this subkey bodies, and the bodies are reflecting the wider thing around the plot. So this little fat blue thing over here, that's a violin body. And what we're going to do with that is set the color. But what we did last time is set the color to the same color for all of the plots, and now we want to have them in different colors because they represent different features. So essentially what we need to do is we need to iterate over this. And now one way of doing it is saying for violin in vplot, and then just setting the color for that violin. But now we don't really get the index that a violin has within this bodies list, which is annoying because we need that index to use in our call list for indexing the first, the second, or the last color. So another thing that we could do instead is say for I in range, then. So this is slightly annoying because it's a bit long. So what we're essentially doing is we're again taking the body. So that's a list with the handle to the violin plot's body. We're checking how long that list is. So this should get us the value of 3. And then we're creating a range from 0 all the way up to 3, not inclusive. So that gives us 0, 1, and 2. Now, those are the exact indices that we need to index the color. So now we could say, and then index I dot set color. So there's a lot of typing. It is clean, it works, but there's a slightly sneaky way that you can use to kind of get around this. It's called 1. So this works, it's nice, it's clean, but I think this might not necessarily be the most readable set of code. So we kind of want to combine this referencing the violin in there and this I in there. So something that kind of ends up looking a bit, if I say violin is body's I, and then I say violin dot set color. So this is already a bit more readable. We know exactly what we're pulling out now. But there's another thing that we could do to this to make it even more readable, and that's to use the enumerate function. And enumerate is essentially a combination of this range len la di la and this for violin in, and then whatever you're looping over list. And it works in the following way. You can say for I, violin in enumerate, that's the function, vplot. There we go. So now what we can do is immediately use this line of code because violin is already predefined in the for loop, and it refers to whatever is at position I in this vplot, this bodies list. And I is also pre-generated within that same for loop, so we can already use that to index the color. So in this way, we write in a slightly clearer, I think, more readable way, the same thing that we've done in a slightly more roundabout way down here. So if we use that, we should end up with 3 slightly differently colored vplots. Also turns out that these are actually quite similar colors, so I might just set them to red, green, and blue instead, so that we actually see a difference between them. There we go. All right. We're going to do something similar for the box plot. So again, I just copied this code from before. We're going to pop into the box plot groups A, B, and C, again as a list. The positions that we're going to pop in are still the same. And we have this nice ability to immediately change the axis labels, because right now we have on the axis still just the normal x-axis, so values, which isn't the cleanest of things. At least you kind of want to get rid of that, because the x-axis now doesn't really have a meaning other than where roughly the thing should be, the group should be. Only the y-axis is actually meaningful in terms of data. So we're going to use that as well. Boop. And then now we've drawn a box plot over the violin plots, and we have them nicely labeled group A, group B, and group C. So now the y-axis is still meaningful data, but the x-axis clearly represents where the groups are. The one annoying thing now is that this orange line is in there for all of the box plots, and it's nicer if that line kind of meshes the body. So what we're going to do is look through all of the lines. So box plot, in the same way as vplot, creates a dictionary. So boxplot creates that dictionary, and we've named that bplot. And one of the things in that dictionary is a list with all of the line elements that make up the median. So those are all those lines that we see over there. And we can set the color in very much the same way. So essentially, I'm just going to rebuild this for loop to make to reflect that same for loop up there. So I'm going to say for I, line in enumerate. Wonderful new thing that we discovered. And then I can just use call. So index that list of colors, the ith place in there, and I'm going to use that color to set the line's color. And then boom. Now each of the lines within the box plot matches the violin colors background. All right, so that was it. That's all of the assignments practice out. There's a few more things you could potentially do with this. So for example, I would strongly recommend setting a axis label like you've seen before. X set Y label, which you could do with a string. So for example, Z score, I think is what we're looking at, because it looks like the SD is about 1. And you can set the font size in these things, which is quite useful to create a slightly larger font on the, oh, that's a misspelling there, isn't it? Typos are literally the death of me. There we go. So now we have a slightly larger font up there, which is quite nice to have. All right. Are there any questions at this point, either about what I just typed or about the things that you've seen throughout any time in the rest of today? All right, doesn't seem like there's any questions. That's grand. So that means that we're now at the end of today's session. Tomorrow's session is going to be, I guess, more exciting if you're into statistics. We're going to do a lot of statistics. So part of that is the standard statistical tests that you'll see in any kind of basic paper. So correlations and difference testing, correlations in all sorts of different ways. So that's both parametric and non-parametric. And then after that, so after that first hour of doing basic statistics, we're also going to look at model fitting, which I think is a slightly more exciting exercise, because you can actually do that in all sorts of wonderful environments, including during experiments, but also in our case in the data analysis afterwards. So we'll be looking at standard regression. After that, we'll look into multivariable regression. And then at the very end of that, we'll also look at nonlinear model fitting. So essentially the type of things that you would be doing if you're fitting like a Q-learning model or literally anything else. We're going to actually focus on visual attention, but that's just the example that we're going. And then tomorrow in the afternoon, we're going to step away from the Jupyter notebooks a bit, and instead I'm going to do a few just walkthroughs of experiment code. So one of the downsides to Jupyter Notebook is that you can't actually use it to create or run the standard psychological experiments that you would normally run on a lab computer. So tomorrow afternoon, we'll have two bits to the sessions. One of them will be looking over how to code an experiment, and the other one will be looking at how to set up your Python environment at home or in the lab, so you can actually have an environment there that you can then use to set up your experiments in. So that will hopefully be useful, and also will be a bit more with me actually demonstrating than it has been so far, which might be less exciting, but at the same time is hopefully a way that we can actually look at experiments without having the option of running things on local computers. All right. With that, thanks for being here. I also have a strong urge to end with like and subscribe when I'm in this kind of environment, but I guess there's no button for that. And I'll see you all tomorrow. Stats are obviously not necessarily the most exciting part of everyone's daily job, but they are a super important part. So it's quite important we know how to do them in Python. I wasn't completely aware of who was going to be the main audience here, and who would have the most recent kind of up-to-date statistical baggage. So some of the workbooks today are kind of a mixture of very basic stats teaching and the actual implementation in Python, which basically means that some of you might unfortunately feel a bit talked down to. That's obviously not the point. Just scroll through all of the basic stats if you think that you don't need a refresher. I basically borrowed some material from my undergraduate course, which can be a great refresher if you're not that deep into the basics anymore. But it can also be very basic if you are still aware of the basics. So what I'll do to start off is just basically share and hopefully refresh some of the things that we did yesterday. So one of the things that we did yesterday was getting to know Numpy or numerical Python, or however you want to call it. And so we did that by importing Numpy into our Python. And then what I'm going to do now is just use it to create some fake data. So we've imported Numpy. I've set two groups. And the idea is that this is fake data, but it's somewhat realistic fake data. So what we'll do is we'll create normal distributions that are slightly different from each other, because that's essentially what we're doing if we're looking for differences. So I have the mean set out here. One of them is going to be set at 0, and the other one is going to be set at 0.5 in relatively arbitrary space. This is within a space where we will give the normal distributions a standard deviation of 1. So to put that into context. The other thing is that we're going to look specifically for related sample situation. So set a covariance matrix for two features essentially, for the feature to be obviously self-correlated, but also correlated with the other feature. So essentially with a mean and covariance structure like this, the groups that we'll have are, I guess, kind of an okay representation for a related samples test. For example, one sample test at time 0 and one sample test at time 1, and maybe something happened in between, and maybe you're trying to test what the difference is of that thing that happened in between. Maybe you want to show a pre-COVID sample and the other one is your post-COVID. All right, so what we learned yesterday is that you can actually create fake data using those properties, using the multivariate normal function within the random module. So we can create this X, in this case, this data set that will have, oh, that's very helpful, that'll have the mean structure that we just devised. So an average of 0 in the first feature and an average of 1 in the second feature. Sorry, 0.5 in the second feature, with the appropriate covariance metrics that we specified, but you can set the size of the sample as well. So if we run this, boop, we see that we have in X there 100 observations on the rows and 2 features on the columns. So basically that's 100 people and 1 measurement at each time point. So let's do some just convenience renaming. Let's call the first one T1. This is where that nice slicing comes in. So essentially, if you wanted to select something of a Numpy array, you take the array name and use the square bracket notations to look at what you want. Now 0 here is the first index along the second dimension. So that will be the first feature that we just simulated, and the colon here means everything in the first dimension. So that'll be all 100 observations that we have. And time 2 will be out of that same X data set. We want again all of the observations, but now we want the second feature. And that's basically our setup now. So essentially we generated random data. Let's do some commenting here. Data with a structure that we predetermined, and then we split the data into 2 points. And now we can start to test for differences between those. So if you remember, the ingredients that we need are some basic statistics. So compute the mean and standard deviation. And you might recall from yesterday that, no, actually, did we do that yesterday? No, I don't think we did. Anyway, Numpy has genius functions for that. So one of them is, let's compute the means for T1 is mean. A function that simply computes the mean. We created one yesterday ourselves. This is basically the very same thing. Because it's a Numpy function, it's a bit quicker than the for loops that we created yesterday within our own functions. So we're just going to use this one instead of our own ones. And we can also compute a mean for T2. That was basically the same thing. So we again use the mean function from Numpy for T2. And then we also want to compute standard deviations. And that's the standard STD function. Boom, there we go. And the same for, there we go. Window, so we can actually see what's happening. There we go. So we have a mean of just under 0 and a mean of 0.6-ish. And then we have SDs that are just under 1 and just over 1. So that actually, shows that we have a pretty decent handle on what we're doing in the data generation, because the whole idea of that multivariate normal is that you can specify the means, which we specified as 0 and 0.5, so we get relatively close to that. And the SDs of that multivariate normal are per default 1. So we actually also get pretty close to that. Great. So what do we do now? After we've got the 2 means and standard deviations, how do we check whether there's a difference between the 2 groups? Does anyone know? I think it's a good thing that there's some stats refresher in the course materials today. So the proper answer to that is we're going to compute a related samples t-test. What we're essentially doing with the t-test is we're trying to compute the related samples t-test is to try to compute whether the difference is meaningful. And just trying to back now and back on the screen sharing. There we go. Boop. So the first thing we'll do is actually compute a difference. So the nice thing is that there we go, that in Numpy, what we learned yesterday as well, is if you have 2 arrays, you can actually subtract the data in one array from the data in the other, which is great. And that was that point-by-point comparison. So if we say the difference is T1 and subtracted from MT2 specifically, then what that should do is for each of the points within the MT1 vector, it subtracts the equivalent point in the MT2 vector. Sorry. So if we now check what this is, we can actually see that we have an average difference of around 0.62. And now we know that difference. We also want to know whether that is actually meaningful. So one of the things we can do again is compute the mean and SD of the difference. MD is Numpy of mean deviation of the difference. There we go. Excellent. All right. So here is that, oh, I messed up the syntax. So the idea here is that we now know that we have a difference between these two groups of around 0.5 and a standard deviation of 0, which seems off, doesn't it? Oh, okay, my bad. We should have been subtracting the vectors, of course, not just the means of the vectors. There we go. That makes way more sense now. Excellent. All right. So we have a average difference, there we go, of 0.63, and we have a standard deviation of that of about 1. So you can already kind of, on a general kind of finger speeds to good feel, I guess, say that, well, 0.6 is quite a large difference with respect to the standard deviation of 1. Normally, you'd compute a t-value for that. T-value, of course, being the mean difference, m divided by the standard error of the mean, or at least by the standard deviation divided by square root of n. So for this, we actually need to know n as well. We preset that, but we can also compute that directly off our vectors, because we learned yesterday that they have a shape. So we had that d vector that we computed. That was just all of the observations and the difference between those two time points. So if we ask for a shape, we should get back the number of observations that we have, n. So then our t formula is basically we need the mean divided by the standard deviation divided by the square root. Which isn't quite the standard error of the mean, but let's call it that anyway. So what we do is we take the standard deviation, we divide that by the square root of n, and then we have that for in our function. And in fact, we can write that t function a bit quicker by just plopping that in here. Okay, so compute one sample t test. There we go. That all works. What I forgot to do is print out the t-value, and our t-value is 2.4. Woo-hoo-hoo! That smells like it might roughly be in the right direction. Oh, sorry, I just saw in the chat that Celine helpfully pointed to the typo from earlier. Thanks. Okay, so the idea here is that we have now a related samples t-test, and essentially what we did is just recombine some of the things we learned yesterday to actually come to that one value. But of course, our lives wouldn't be our lives if they didn't revolve dramatically around p-values. So now we need a p-value with this t statistic, and that's where actually the new stuff comes in from today. So in order to do that, what we're going to need is the SciPy module, which is short for Scientific Python. And it's a really, really useful module that's kind of within the same ecosystem as Numpy is. And from the SciPy module, we're specifically going to get the statistics module. So what I'm going to say is import SciPy stats. There's just a habit of S to save, and then I'm actually in a place where I want to save. Okay, so we import SciPy.stats. And SciPy.stats has very many very useful things, but one of the, I guess, most useful of things is that it has distributions built in there. So we can now compute whether our t-value is expected or not within a t thing, a t distribution. Okay, so for that we need two variables, or at least two main things. The first one being an actual t distribution representation, and the second one being the degrees of freedom, because that's what primarily determines how normally distributed a t-distribution is. For those of you who forgot it, a t-distribution essentially is a normal distribution, but it's penalized and kind of flattened the fewer degrees of freedom you have. So first we're going to say compute the degrees of freedom, which is quite simple. It's n minus 1. Yeah, there we go. And then what we can say is I want to create a distribution. So that distribution around the x-axis will have a bunch of values, and then around the y-axis will have the actual number of observations, or the probability density rather in this case. So let's say compute maybe it's better one. Construct a distribution. Sorry, t distribution, and then we can use the scipy t f. There we go. So scipy.stats comes with a few built-in distributions. So one of them is the t distribution, and its PDF function here is the probability density. So it's a probability density function, PDF. Now I need two things for that. One was the x-axis. So let's give it an x-axis. We can use one of the functions that we learned yesterday for that. So numpy.range. Let's say maybe -5 to +5 in steps of 0.01, just small steps. Now what we can do for each of these values is compute the probability density at each of those points. That's what that PDF function is for. So I'm going to chuck in there the x-axis. I'm going to say df is n minus 1, and I don't even have to compute it up here either. And I think that should work. There we go. So every time I run this multivariate normal is also rerun, which is why the values just jump up and down a bit. Anyway, I now have my t-distribution, and now I can use one of those other things I learned yesterday, the matplotlib package. I'm going to import that one as well. So from matplotlib, and then pyplot. So we have the x values, so sorry, the x-axis. We have the distribution, and I want to just portray this as a single line. I can set the line width to say 3, and I can set the color to green. Green is a nice color. And then if I run my code again, we should get a neat t-distribution. Yeah, there we go. Okay. So this is a t-distribution. Had I put in a slightly different set of degrees of freedom, what you get is a slightly different distribution that is a bit flatter or even a bit sharper, depending on whether I have fewer or more degrees of freedom. And now the crucial question that we had was our t-value, where on this distribution is that t-value? And one neat thing that we can do using pyplot is create a xv line. There we go. So vertical line on the axis, and we want to have that vertical line exactly where the t-value is. So that would be t-val. There we go. Line width of 3. Let's set some and the color. I'm switching between keyboards nonstop now, and it's really not good for my precision typing. There we go. All right, a vertical line where the t-value is. Boom. Excellent. Whoa, that's well beyond the normal distribution. So essentially, let's extend that a bit so we can actually keep that in scope next time. So now the objective of statistics is to see how surprising this value is. For that, you compute the density, or at least the area under the curve up until here, so that you know exactly how likely it is that you find a value that is equal or lower than this, and then you subtract that from 1. There are functions for that as well. So this is, so value, okay, so we want to know at first, using the t's cumulative density function, how likely it is that you find a value lower than this. So that would be t-val and df is 1. Excellent. And then we want to subtract that value from 1. So this is the likelihood the probability that you find a value that is equal to or lower, that's lower than the t-value. If you subtracted it from 1, you find the probability that you have a value that is equal to or higher. If we're doing two-tailed testing, obviously you need to multiply it by 2 and actually just take the absolute value of this. But for now, this should be enough. And then print b. There we go. And we find a p-value of astronomically low, 1.8 to the times 10 to the power of -6. It's a really, really small value. So that might be a significant difference that we found. Now, before you think, God, this is really quite complicated in Python, why am I switching again? There's one other way in which you could have computed this from the start, which is to say, you could have imported this t-test rel function and then chucked in the 2 different groups in there. And that should have done very much the same thing. Again, slightly different values because we re-randomize everything, but we find a t-value and a p-value as well, just using this one line of code instead of going through the entire previous FAF. Excellent. So that and more is what is in the slide, or at least in the workbook this morning. And then this afternoon, we're going to go through slightly less boring, slightly more exciting statistics, specifically model fitting. So with that in mind, I'm going to just paste all of the relevant links into the chat here again. It's the same as where we were yesterday. So again, same kind of difference. If you are in the lucky position of a Google account, please use Google Colab. And we're doing the same thing with the slightly extra thing that you need to do for getting the files actually loaded into Google Colab. All of that should be in the worksheet though. So the same kind of bit of code that you used yesterday to log into your Google Drive and then be able to pull files from there should be in here again. If you didn't upload all of the files to your drive yesterday, you will need to do that because there's a few different files that we'll be working with this morning. All of the instructions are also in the GitHub link I in the thing. Then I'll also give you the direct links. Over. So this is the direct link for Colab. There we go. And then I'll also paste in there the direct link to Binder. And with Binder, start up the 5th one already. Oh, right. As per usual, we'll be here to answer any questions. For example, like why I didn't set the difference of degrees of freedom in the statistics computation, which I should have. But the bottom line is go through these sheets, and if you run into any problems, give me a shout or paste it in the chat over here. And have fun, good luck, etc. As before, by the way, give me a shout when you finish the worksheet. So if you come to the end of the 05 statistics, blah, 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 just send me a direct message on this. So I'll let you guys run through yourselves and then we'll do a central bit afterwards to check out the assignments. But the crucial thing that Sophia just pointed out, thanks for that, is that there's a small bug in the script up here. So just read this in your own time. But when you get to the setting of the file name and you are on Google Colab, I forgot the double quotes at the end of this. So make sure that you add those so that the string is complete, and then you don't have to find out where the syntax errors are coming from. Well spotted, thanks for that. I'll fix it in the source material as well, but it'll take a while before that. Cool, all right, have fun. If you do run into any issues, do give me a shout. And especially if you run into any like typos and bugs, definitely let me know, because I can update the material so that when you're looking at these well in the future and forgot all about it, that they are all correct and without all of the just but actually that double quote is missing from the other Google Colab file names as well. So you just pay close attention to those file names. Can I just do a quick check on who is finished? Pop your thumbs up in there. Excellent. All right. All right. Checking in again to see how many people have finished already. Just pop your little thumbs up in the Zoom if you are. All right. So that's a handful of people. I think what we'll do is we'll use the rest of this hour, so up until noon, to just finish the assignment. And then after lunch, we'll come back to it. So lunch break is again from noon to 1 p.m. as it was yesterday. And then when we come back after lunch, we'll have a quick look at the assignments for the model fitting and statistics from this morning. And then after we're done with that, we're basically just going to run through experimental logic and building experiments. That will be mostly demo because unfortunately the Jupyter kind of environment isn't really suitable for actually running experiments. So it'll be slightly less you doing stuff and slightly more you watching me do stuff. But c'est ça. So I'll stick around obviously for some time so that if you do run into any questions for the model fitting sheet, you're very welcome to ask. Just take your time finishing that, and then we can start again at 1 p.m. For the afternoon session. And welcome back, most people. I'm going to wait for a wee bit longer until everyone joins back in again. And after that, we're going to get started with experiment building. Woo! All right, sorry, I'm still muted. Back in, there we go. All right, as Tim just helpfully pointed out, we're kind of going straight onto the experiment yet because there's the answers to the assignments to run still. It's for my benefit. How many people did end up finishing the assignment for now? Just hit a little thumbs up in it. I see a few people, quite a few people. That's fine. All right, so I just opened the model fitting notebook and to drive, and then let's go scroll down all the way to the fitting for the final assignment, because we'll need the data for that. All right, so we're loading all the data, plotting all the figures. I'm just running through all of these things so that I actually have all of the things that I assume to be computed, and also all of these defined. One confusing thing here that some more people picked up on is that if you fit these two models to the data, they kind of overlap. And that was an interesting thing because you expect both of them to appear, and yet it seems like only one of them appears. If you look at the fits, they actually are slightly different. It's just that in the way that we defined a model, one of the parameters was allowed to be, but the one parameter that we fitted was allowed to be in any given space. And then divided by a certain number of stimuli. So with only one set of numbers of stimuli around, we can just multiply that limited C parameter by however many stimuli we used, and then we end up with the unlimited C parameter. So essentially, you could transform one equation into the other, essentially, by just manipulating the parameter there, which is kind of it's a limit to how we experimented this. So with only 3 stimuli in our experiment, but also it is a limitation when you do model fitting, because if you don't specify your model or don't necessarily think about how your model is specified, and you do allow for these kind of things to occur, then certain models can actually appear completely equally plausible. And that's just, that's because they are equally plausible if you don't define any bounds on where your parameters are allowed. It's not necessarily a wrong thing, and in this case, there are different underlying theoretical considerations for both. So it's still an interesting thing if you just look at the parameter fits, but that's why they completely off. Scrolling down a bit, adding those other models, excellent, and then we. Okay, so the first assignment was to run all of the models, or at least model 1 and model 3 for all of the individual participants. Because what we did before was compute this Bayesian information criterion for the individual models, but not for the individual participants. So we just computed them off the basis of the average M from all of them. All of them being all of the participants. So we computed the average of all participants, and then we just fitted the models to that average. And a slightly different way of doing things, and arguably slightly better way of doing things, is not fitting your model to the average across participants, but fitting your model to each individual's average. And one benefit is that you get a parameter estimate for each individual, which is very sensible because some individuals will have a bigger processing capacity in this case than others. So that in itself can be an interesting thing. And in addition to that, there's also the idea that if you have, for example, a step function, but that step function is a bit delayed in some people compared to others, the average is going to look like a really nice sigmoid. So your average is actually not necessarily reflected in each of the individuals. So if your model was a sigmoid function, it'll fit perfectly to your average data, but it won't fit very nicely to your individuals because they all have a step function. So you'll never actually find the right model there if you're just looking at the overall averages, I guess, compared to the individuals. So an alternative thing to do is to fit your model to each of the individuals independently. And that was the first assignment here, specifically model 1 and model 3. So model 1 was that capacity limited one, and model 3 was a capacity limited one, but we also included a wee bit of space and time before somebody perceived a stimulus. So basically, model 1 starts at t0 is 0, and model 3 starts at t0 is a free parameter. Your data was all in the data variable, so if you want to know the number of participants, check data.shape1 in this case. So that's our first bit of thing to do. And then we wanted to create a Numpy array with the BIC values, because we are computing one BIC value for every participant, but also for every model. So what we need is BIC. And let's start with zeros. This is a bit tricky. So if you create these empty-ish kind of matrices from the start, one thing you always want to make sure is that you fill out each and every single part of it. Because if not, the values that you've missed and failed to fill out will remain what they were at the start, so 0 in this case. And it will greatly depend on what the actual values are that you add in, whether that's an issue or not. But in this case, it could be an issue because you might think arbitrarily that this BIC that you potentially missed was actually a value of 0, which is potentially very different from these BIC values that you might end up with. And then you might, artificially think that model is a good fit, even if it wasn't really, because you simply forgot to fit. So always be a bit careful. One trick you can do is, after you've initialized this, just multiply everything with NaN, which is not a number. I'll show that in a second. For now, let's create a matrix of zeros. So we wanted it to have a particular shape. And let's say shape is and participant 2 shape. And we also want it to be of a float data type. And the little trick that I just talked about is so multiplying it by NaN, which is not a number. Now, if you do any kind of computation with a matrix that has nans in there, not the numbers in there, you'll usually escalate the nan to higher. So if you compute a mean, for example, you get a nan instead of the actual mean, if there's even one nan in there. So that's a really nice way of finding out whether there is a value in there that you might have forgotten. Oh, right. So our objective was to loop through all the models. I already pre-built the for loop to do that. So it was the same enumerate function that we were introduced to last time. It gives you back both the values and the index number of the value. So the value will be a model number. So it'll be 1 on the first iteration tree, and the second iteration, I will be 0 and 1. 0 for the first iteration and 1 for the second. Then we get the model number, and then we look through all the participants. That was also pre-filled out, and then we fit whatever the current model is. And I'm going to borrow a bit from the previous code because it already had the fitting function in there, so we might as well copy paste. And then adjust as necessary. All right, so the outcome that we want to get was through that use of the minimize function, or to minimize the number of residuals. These were the starting values that we're just going to guess should be around zeros. And then the arguments that went in there were the number of stimuli, the exposure durations that we use on the x-axis. And in this case, it's not the mean of the of all the data, but we wanted to have the specific participants' data. So we need the data variable, and we need to find out the specific participant number in there. So the exposure durations were in the first dimension and the participants in the second dimension. So we take all of the exposure durations for participant J, J because that was the range that we were looping through. And then this was the model number that went in there. And the method is a specific thing for the fitting system that we can just use the same. All right, so this would basically look through all participants and fit a model. And then come back with the best parameters for that model. So now we want to compute how well that model actually fits in the best fitting scenario. So I'm going to again borrow a bit back. We want the residual sum of squares computed. There we go. All right, now outcome we can just use because it's produced here. Outcome.x was all the parameter estimates. So the first one in there will be the capacity. The second one in there will be T0. Number of stimuli is the same. Exposure duration are the same. And here M, again, we need to update to the actual data associated with this participant. So within the data variable, across all of the exposure durations, but only for participant J. And this was, again, the model number, which specified which model to grab. N was important because that's the number of, not participants in this case, but the number of exposure durations that we had, so the number of observations that we actually have for this participant. We actually have more observations because all of these averages that we have for, all of these values that we have for the participants are actually already an average of our trials. So this might not be, but we're just going to run with it. And then I'm going to also copy that BIC computation because CBA for typing myself. All right, so just checking whether that BIC computation is fine. So we chuck in there the number of observations we have that we just recomputed, so that's fine. We chuck in the sum of squares, sum of residual squares, there we go. And we recomputed that for this particular participant, so that's great, we have that. The N again, and then the K is the number of parameters, and we selected that on the basis of what model number we were using that was pre-filled. The only thing now is that we don't want to just overwrite the BIC. So we created this array before to keep every BIC in. So we want to add our current BIC to that specific matrix. And the shape was first number of participants and then the model. So what we should be adding is BIC J, I. So J for the participant number and I for the model index, essentially. And then if we run this, we should be able to grab the average BIC for all participants, but also compute the difference for the BICs for each of the participants. So for example, the DBIC should be for each of the individual participants, BIC everything, 0. So this is for all of the participants in that BIC matrix, but for the first model, minus BIC everything, 1. So again, the BIC matrix for all participants only in the first one. So DBIC will now be a single vector that will have as many values in there as we have participants. And what we're really interested in is the average of that DBIC. Oh, sorry, the sum. There we go. There we go. if we want to be real neat about it, we can also just round that form. We don't really need that many digits, do we? Excellent. All right, so if we run that, which should be running through all of the individual participants, and we see that there's a decent DBIC for each of the participants individually. And when you're doing model fitting, this is one of the things that you kind of want to look at, because for some participants, randomly, one of the models could occasionally fit really well. You have these really high kind of individual outliers almost. And it's always a bit tricky to see whether those are really weighing quite hard on the sum DBIC. But in this case, it seems actually for each of the participants, the difference was in the same direction, which isn't necessarily that weird of a thing, because it's all fake data that was generated using the models that we're trying to fit right now. So yeah, this is the sum across all participants, which basically tells you that there's a heck of a lot of evidence in favor of the second model, so the model that had both the T0 and the C parameter. Any questions on that first assignment? An assignment renders pretty poorly in Google Colab. Imagine that all of those nested lists have their own different, typing. So the idea is that we want to compute power through a simulation. So what we will be going to do is we're going to select a few cones D effect sizes, a few sample sizes, because we know that increasing the sample size improves your power, and we also know that at higher cones D, or at least higher effect sizes in general, usually you have a higher power. So that's essentially what we're going to do. We're going to just try a bunch of different cones D sample size combinations and see whether we can actually compute power through a simulation. In this case, a simulation is a randomly selected set of samples from a normal distribution, and we're going to compare that to another randomly selected set of samples from a normal distribution. And we're going to manipulate those two distributions so that they are exactly the distance away that we set as the effect size. So first, let's say import numpy from numpy.stats import the t-test ind, which is the independent samples t-test that we're going to use, and also from matplotlib, there we go, import matplot, there we go. And then the first thing to set is the effect sizes. So we wanted to test 0.3, 0.5, and 0.8. And the second thing is to set the sample sizes, because we wanted to test 10, 20, 50, 100, and 1000 even. Wow. And we're going to set our significance threshold at 0.05. Excellent. Now, another thing we want to do is creating a new empty plot so that we can add a line in that plot whenever we complete the computations for a new effect size. What you normally do for power plots is on the y-axis you plot the power, so the number of, or at least the proportion of significant tests. And then on the x-axis, you plot the number of participants that were in your samples for that test. So essentially what we're going to try and do is create one line for each of the effect sizes, and that line goes across all of the sample sizes on the x. Excellent. So now the objective was to loop for I, comma, d enumerate size. There we go. And before I continue this, let's also create a empty array that we store the power in. And that array should contain floating point numbers between 0 and 1, because that's what our power means. And the shape should be enough so that we can fit all of the effect sizes and all of the sample sizes in the same matrix. So we're going to make the shape dependent on how long the effect size and how long the sample size lists are. There we go. So this should be 3 by 5. But the neat thing about not just writing 3 and 5 is that now if we make any changes to the effect size in the sample size list, they are automatically picked up by the rest of our code. So we don't have to actually manually do any kind of extra typing there. So my data type to float there. Excellent. So now that we have this, we can actually fill it out during the for loops because that will be quite important. So essentially we have our first for loop, 1, 2, 3, 4. And then our second for loop is for j, comma, n for number of participants in this case, and enumerates the, there we go. So do power. And then after we compute the power, which we're going to fill out in a second, we're going to store the power in that power I, comma, j. There we go. Because I was the effect size index and j was the sample size index. So this is where we want to store that power. Excellent. I'm just typing that out right now. I obviously still need to actually complete this because I don't have anything to compute my power over. But it sometimes helps to kind of do that before you start adding complexity to your for loops. Because within this for loop, we're going to run through all of the simulations. So for, let's call it k in range 1000 is the number of simulations. And obviously a cleaner way of doing it is actually saying and simulate and making that into a variable that you set at the very start. So that, again, you can change it by just typing something on the top without having to deal with the rest of your code. And then for each of the simulations, what we want to do is create 2 random groups. Let's say group A is numpy.random.rand n. In this case, we use the rand n function because we're going to create a normal distribution, and we wanted to have n people within that sample. So n was created in this for loop, so we can refer back to that. Group B is the very same, so I'm just going to copy that over, and then boom. We don't actually have to do much about this because both of these were already per default have a standard deviation of 1. So the only thing we need to do is make sure that we have a difference in there. So let's make group B slightly different from group A. So currently both of them per default start off at a mean of 0, and we want the mean difference to be the, essentially Cohen's d because they're already normalized space. They both have an SD of 1. So we can just say plus the effect size of d, which we created in our first for loop. So now we have one normal distribution around 0, one normal distribution around 0.3, 0.5, or 0.8. And what we can do now is create at least test whether they are, in this particular run, actually significantly different from each other. They might be, they might not be. It really depends on just the random numbers, and that's actually kind of the crux of this. So t, p is t test underscore independent of a, comma. And then the only thing we want to know is whether the p-value is smaller than alpha. And one thing that we could do is just compute, or at least hold a, start with a vector of significance value. So for each of the iterations, that will have one value. So we can set this, for example, to and simulations. That is what the length should be. And we can set the data type to Boolean because we just want this one to be true when there was a significant result, or false when there wasn't a significant result. And then we can say if p is smaller than alpha, which is our statistical significance, sig of k, because that was the created in the for loop here. Say k is true. We don't have to do anything in the other case because we started everything with 0. So this is already pre-initialized at all false values. So the going assumption is everything is false from the start. A bit like in science, I guess. And then we update everything to true. That is actually a significant result. And now we also know what to do to compute that power that we pre-flagged here, because after 1,000 computations of significance, the proportion of significant results there is the power, or the estimated power. So what we can do is say, well, we want the sum of this sig matrix. I'm going to use a little trick here. So we can say n significant is the sum of sig. We're going to use a little trick because this is all Booleans, and Booleans are represented as a 0 or a 1. So if I take the sum of a bunch of Booleans, I actually take the sum of the number of true values in there. And if you want to really formally do that, you first cast them as integers so that all of the falses in there are transformed to zeros and all of the trues in there are transformed to ones. Strictly speaking, you don't have to do this because this automatically is already the case. But, you know, just for neat programming sake, you might want to do this. Okay. And then the power is the number of significant values divided by the total number of simulations that we ran. So this is the proportion of significant values. And then we want to plot that line as well. That's the other thing. So after we have the power, so there's a small issue with Google Colab, it seems, which is that its default tabs is 2 spaces, whereas the default tab that I would recommend is 4 spaces. So that's what I was fixing just now. There we go. All right, so we want to plot the power for specifically this effect size. So we can say is x.plot. We want to plot along the the x-axis, which was all of the sample sizes. So we can say the sample size is the x values and the y values is the power. But very specifically, the power for this specific effect size along all the sample sizes. We want to make that into a line. We want to make the line width 3, like a bit thicker. And the label we can set to d equals d. There we go. Excellent. I'm just going to put that roughly. Those little breaks in there, they don't mean anything for the code. They just make the code a bit more readable if you just look at it in one glance. Excellent. So we've created a plot. We've computed all the power in there. We plot all the lines. And now the objective was to, I think, save the figure. Oh, no, I didn't even tell you to do that. Ah, well, always a good thing to make the plot a bit neater by adding X and Y labels. So let's do that as well. Yes, the answers for this are available. Actually, they're already on GitHub. They're the same document name _ capital answers for those who struggle to write along. Okay, so the X label was sample size, x.set _ y label. Oh, that horribly. Wow, cannot type for the life of me. Power. And then also we want to introduce a Legrand. And then there we go. This takes a while because it loops through all of those different simulations and produces this. Huh. Okay, well, it makes you wonder where one of those lines went. It should be in there somewhere. But basically what we can see from this is that the power essentially increases over sample sizes. Actually, you know what? Let's set those sample sizes a bit lower so that, there we go, we can actually fit them all on the same screen. From 10 all the way to, let's say, 210 steps of 10. There we go. And then, boom, that's going to take a wee bit longer. Okay. As a nice little example, this might be a bit overkill. The point is that you can actually do this quite well. And, oh, I think I see what's going on. So there we go. So probably what's happening is that in the background, I might secretly be running Python 2. So this integer by integer division is actually resulting in an integer. So I'm going to make sure that this is a float and therefore that the result should also be and then run again. And then hopefully we have actual smooth curves rather than step curves. Yes, there we go. Also, excellent. So essentially what we're seeing here is that the larger your sample is, the higher your power is, and the higher your effect size is, the higher your power is as well. So there's a really neat way of running some really simple back of the envelope simulations that can be quite useful in some situations, but in this case it was primarily just a useful use case for looking at a few of the things that we've seen yesterday and today and just combining them all and practicing a bit. Excellent. All right. So far, so good. Are there any questions on that or anything that we've seen in the past two? Great. It's wonderful. It's also super clear. Then we're going to go on and move to experimentation. So one thing I did just before is install Anaconda on my own laptop, specifically this one. Just for background things, you might see me blunder into a few issues just in the next hour and a half. The downside of my work habit is that I have one computer that I do most of my development on. It's a Linux system. The computers in the lab are all Windows systems, so I'm reasonably comfortable with both of those systems, developing Python code for that. The computer that I'm currently talking to you on is a Mac, and Macs suck like really badly. And the annoying thing is I need it because iOS is one of our development targets. So for all of non-Python programming, I actually need this thing to work. But it's also kind of hard to run Zoom on Linux. So I'm also using this for Zoom, which basically means that I'm now locked into a system that I don't fully understand for showing you how to do coding in Python. So there might be some weird mistakes that I run into over time. We'll find out very soon. There's a few things that I prepared because what I'm going to show you is how you would normally go about creating or at least how one could go about creating an experiment in Python. And the idea is that I installed Anaconda, and then there's a few things that you kind of want to know about Anaconda. The first one is that it comes with Spider built in. So that's this wonderful environment here. Looks a bit like the MATLAB editor, and it also looks a bit like the RStudio editor, if you're familiar with either of those. On the left here, we have the script that we're currently working on and a few tabs of other scripts that we might have. So these essentially are just scripts that you can do whatever you want in. On the top right, we have a little information window, and that can be really helpful. It basically tries to keep up with whatever you're doing in either the editor or the console or both. And then it gives you tool tips or essentially just, whenever you type a function, it can say, well, this is what the function's information is. This is what the arguments are that it expects. And this is how you deal with those. And then we have a console on the bottom right. And the console is essentially, it runs your code. So if you say, A is 3, B is 2, print A plus B, and you hit the run button, it runs in the current console. You see 5's printed out, and also the variables A and B are now known in the console. So this can be really useful if you're wanting to do some kind of online debugging of your code. You can literally just do whatever here and then run in the console. Excellent. So that is one of the really useful things to know about Anaconda. The other is that it comes built in with a bunch of really a large bunch really of external modules. So if I say import Numpy, it already works. I didn't actually have to install that, which is quite great because that can be a bit of a faff if you have to build up your entire environment from scratch. The one thing I will say is that the experimental libraries that we normally use aren't included in Anaconda. It's because we're kind of a niche field in experimental psychology. Not all of our tools are generally available, or at least are useful if they are generally available. Is basically the problem. So one of the things you might need to do is actually add those tools into your Anaconda distribution. So let's say you've downloaded this whole thing. The next thing you want to do is find where your terminal is. And now your terminal is not something special that came with Anaconda. This is built into your own computer. It's called terminal if you are using if you're using Linux or Mac OS. It's called command prompt if you're using Windows. And you might be familiar with it, at which point, apologies for talking down to you. You might not be familiar with it. And then this is essentially what you end up if you start. So this is very useful because it allows you to kind of directly talk to your computer without any kind of buttons in the way. And it's also something we'll be using today because one of the things we can do with this is updating packages in our Python distribution. So this is going to be specific to your installation. On my computer, my Anaconda is in this location, and my pip, which is the Python, basically a tool for installing Python packages, is also in there. Sometimes, actually many times, that is reduced to simply pip or pip3 that you can also call on your, in this case, yeah, it is set properly. Okay, so one thing you want to do if you start off with just a blank new Anaconda distribution is say pip install. This is basically telling Python, yo, I want to use the little utility program that you have called pip to install the following package, Pygame. Pygame is one of those packages that we want. In my case, it says, oh, you've already satisfied that, because that's what I did during the lunch break. The other thing that we want is PsychoPy, which is also already installed. But for PsychoPy, there's a few other dependencies. So essentially what you're doing here is saying, hey, I want to install this package. Then the package manager will tell you, actually, you don't just need this package. This package needs some other packages as well. And then it'll find all of the dependencies for you. So that's why there's so much output in here. And then the other thing that we want is pip install Python Pygase, which also already satisfied. Okay, so Pygame is a really useful library that allows you to build video games, essentially. It's used a lot for 2D platformers. But the nice thing about video games is they're really close to experiments that we use in psychology. Then PsychoPy is a library specifically designed to create experiments in psychology. There's a few built-in tools that are really useful for vision science, for example. There's these Gabor ratings and noise ratings and all sorts of flashy color space recomputers. That's cool. And then Pygase, that final one, is a library that kind of is on top of those two and uses either Pygame or PsychoPy to do stuff. But the nice thing in there is that there's also Pygase is specifically designed for baking eye tracking experiments. And we're going to use it today because I think it's also more usable than the other two if you just want to build a simple experiment. I would think that I wrote this, so a huge disclaimer on there. You can also use PsychoPy or Pygame if you prefer. The reason both of those things are supported is that Pygame will run on literally anything. You can run it on an old Nokia. I'm assuming that somebody built a distribution for potatoes as well. It literally runs on anything. And PsychoPy, at least when I started programming, it had some issues with really old video cards, which were exactly the ones that we used in the lab space then. So we kind of had to opt for, well, use PsychoPy if we have the option to, but fall back on Pygame if we don't. So both of those were then supported, and that's kind of still the case. All right, so now that we have those two, the other thing that we need is the path to our Python. And that might seem a bit silly because all of the things we do is Python, like what we have in the background here, Spider, that's Python. With the path to Python, I specifically mean the Python executable that is somewhere on your computer. On Windows, it's called python.exe, and on Linux and Mac, it's just called Python. And in my case, you know what? Let's just start a new shell so that it's nice and clean and fresh. In my case, I can find Python in /Anaconda3/bin/Python. And the reason I know this works is if I hit enter now, I am suddenly inside of Python. So this tells me that I'm in Python 3.8.3, and I can say import Pygame to test. Oh yeah, I have Pygame in here. Excellent. Okay, now the reason that this is important is that I'm going to essentially do what I would otherwise do in Spider outside of my code editor. The reason for that is very specific to programming experiments. So this is not something that you might always want to do, but it is something that I want to do right now, because if I run an experiment from inside of my editor, Spider is already a Python process running with some kind of fluffy side bits on the editing front. So there's already some graphical stuff going on here. And if I run my experiment in here, it basically means I'm kind of nesting different Python processes in each other. The one downside to that is that having this IDE, this editor in the background, might introduce some timing issues. It might not. I haven't actually fully tested that on this particular system, so it might well not. But the much more practical issue is that if I run into any errors during the experiment, which I will definitely do if I'm just programming the experiment from the start, this is not the safest environment to be in. Very often, if you have something on the full screen, because that's what you do in an experiment, and an error occurs, and the error is popped up in this console window, the experiment display that's on full screen, capturing literally the entire screen and blocking everything else, is then unfortunately not closed down. So now I'm kind of blind and have to, with my keyboard, try to find the console in the background, try to kill the process in there. It's a whole hassle. Whereas if I run my experiment from the terminal, if there is an error that pops in, everything is closed down automatically, my window comes down, and I can actually see what the error message is. Which is why I'll be running from the terminal to say, start the experiment from here. So that's why I'm going to use this opt anaconda in this case. It doesn't really matter, but this Python executable for. This is where it is on my computer. It's going to be in a different place on your computer, quite likely. On Windows, it's very likely under C and then \anaconda \. Sometimes it's in there, sometimes it's Python. So just search your computer for python.exe or for Python specifically if you want. Cool. Then the other thing of preparation is that I have in my files, I created this folder for the example experiment. That's what we're going to build now. And in that experiment, I have two things. Ignore the PyCache for a second, because that's automatically created, and we're going to ignore that because I didn't make it. So constants.py is one of my files, and experiment.py is my other file. Those two files are specific to Pygaze experiments. Essentially, what you do is you program all your experimental logic in the experiment.py file. And then all of the things that are potentially different between computers, or you might want to change, basically the settings for your experiment, you set it in constants.py. The reason for that is very practical. You don't want to scroll all the way through your potentially hundreds of lines long experiment if you just want to change how many stimuli you're presenting. You just want to say, I'm going to present one stimulus extra. I open my constants file, set n stimuli to 3 instead of 2, and then boom, I'm done. I don't have to bother with the experimental logic from that point on. So it's a really nice way of kind of distinguishing settings from that you want to maybe edit at some point, and the experimental logic on the other. So I opened both of those files in my Spider editor. And then the other thing I need to do is in my terminal, change my working directory to where we are here. So that directory is right here. I just got that from basically the experiment, and you can say, whoop, get info. Just right click on the file to get the same info on Windows. And then I'm going to open my terminal. I'm going to say cd for change directory. I'm going to paste the directory name that I just copied in there. And just to double check whether I'm in the right place, yes. So ls, or if you're on Microsoft, if you're on Windows, use dir. It just gets all the files in your directory. So in my case, it's constants and experiments, and that's exactly where I want to be. Excellent. So now that I'm here, what I can do is say /alt/ bin / Python, and I can say, use this Python thing to start my experiment.py. So it's essentially saying, ignore all of that at the start. I'm just saying, I'm going to use Python, the executable, to run the script file that I wrote, experiment.py. And now nothing happens because I didn't actually do anything in that experiment file. But if I were to add something to this experiment file, so we're in Spider now, and say print, there we go. So one thing I could do is run it in here, but I said we're not going to run it in here. We're now going to run it through the console. So now if I run that file again, I get, hi, this is working. So that's great. Everything is working in the background. As per usual, if you have any questions, just shout. I'm just going to steamroll on and then see where we end up. But do stop me if you find something confusing or want some extra info or whatever. All right, so we're going to build this experiment. We're going to use Pygaze from there. Pygaze has a few different classes built in, and one of those classes is the display. Display is essentially something that you can use to present stuff on your screen, your computer screen, your display. So I'm going to need to import that. So I'm going to say from pygaze.display import display. And now I need to initialize it. So I can say this. You can also call this Harry or literally whatever you want, and initialize the display there. Now, one of the cool things about Pygaze is if I have this constants file, which is the other file that I had made, as long as they're in the same directory, running your experiment will automatically find your constants file and will pick up certain keywords from there. So one of those keywords is disp size in all caps. It's all caps because it's a constant, and that's kind of a programming convention that you normally write constants in all caps. And a disp size is a tuple that has the width of your screen in pixels and the height of your screen in pixels. So my screen happens to be 1440 pixels by 900 pixels. So I've already set that. And then whenever I start this display, it automatically picks up my display size from that constants file. So it already knows what to do. The alternative would be to set this size in here to a certain value. So I could also do this, for example. The reason I don't do that is because if I move this experiment from this computer to my lab computer, where my display size might be slightly different, I don't want to have to go into my experiment code to change it. So instead, I set it in my constants so that I have all of the variables that I might want to change at some point in the same space. All right, so display opens the display item. And then let's see what happens if I run my script now. Actually, before I do that, at the end of the experiment, close the display. One thing you don't want to do is leave your display open. So after we create the display, we can also close the display. Good practice, and also means that you don't get a gray screen full on. So now if I run this to my terminal, I should see a very brief flash of a display coming up and then going down again. Just for my, could anyone see what was actually happening full screen? Because I'm not entirely sure whether Zoom properly does the screen sharing there. What happened was a gray screen popped up and then went down again. Was that visible? Just thumbs up if you could see it. Excellent, great, thanks very much for that. That's grand, because then we can actually do this without my having to explain at every single screen what has happened. Okay, so this is a pretty poor experiment. It's just a gray full screen and then off again. So one thing we want to do is create some stimuli in there. So one of the ways to do that is not to draw directly in a display. If you do that, then whenever you want to actually update your display at a high frequency, for example, you want the stimulus on for just one frame, like 17-ish milliseconds, and then off again, can be really hard to create that and write that on the fly. So one of the ways that you might want to subvert that is creating a screen beforehand and then doing all of your computation to draw that screen beforehand and then display that. So we need to prepare a few screens essentially that we can then show in rapid succession later on to just keep experimental timing correct. So one thing we can do is create a fixation screen. For that, we need a screen class, which is also in Pygaze. So I'm just saying from Pygaze.screen. Screen. There we go. All right, so I'm just going to call this fix_screen. And the way you set that up is by creating this new instance of a screen. The nice thing about this is that, again, it just automatically detects the display size that it needs to be from the constants, which is brilliant because then I don't have to change anything. I can just say, I want a screen here. It also picks up a few other things, and two of those things, so I'm going to open a constants again now. Two of those things are the BGC for background color and FGC for foreground color. And the default for the background color, as you just saw, is gray. So that's 127, 127, and 127. These are, again, RGB triplets. The values they can get is between 0 and 255. I can also set these to 0, 0, and 0, and I have a really mysterious black screen. And my foreground color I can set as well. So I can set this, for example, to 255, 255, 255, and then I have a white foreground color. So that's already picked up, and the background and foreground colors are kind of technical terms. They also are kind of self-explanatory. The background color is whatever the background is, and the foreground color is, for example, if you draw text or draw a line or draw a fixation plus on the screen, they will appear in that foreground color. So if I say to my fixation screen, hey, screen, could you perchance draw a fixation? I would like that fixation type to be a cross, and I would like the pen width, so the line width, to be about 3 pixels wide, and then I would like the diameter to be, what should we say, 25, maybe, something like that. Excellent. So now I've created a fixation screen, which starts off as a blank screen after I initialize it. And then I can use its method for drawing fixations, which is already built in, to actually draw a fixation cross on there. It's more like a plus, actually, if you set it across. But that's the kind of standard thing. You can also say, I would like it to be a dot, and then it creates this circle within a circle. That is also quite a nice fixation marker. I'm going to go with the slightly more old school fixation cross now. There's a few more other things to this. You can also say color is something. We're not going to do that now because we already set this automatic foreground color, and I would just like it to be the foreground. Okay, I'm going to run my experiment again and see that absolutely nothing happens other than creating this nice gray screen, which is a black screen now because I altered the background color. And other than that, I see nothing, because one thing I haven't actually done is present this fixation screen to the display. So in order to do that, we need to show it. So fill the display with the screen. And for that, I need the display again, and I specifically need the fill method. So this method allows me to pass the screen to the display. Excellent. So now it is, after calling this, it's kind of prepared in the background. So your display is now very ready to start showing the screen. It's not showing it yet, though. For that, what we need to do is call the this.show method. So this one fills it in the background and gets it ready. The show function actually presents it to the display. And one of the nice things is that I get a timestamp. So I can say T1 is, and this timestamp will be in milliseconds since the start of the experiment. How many milliseconds exactly that is isn't super important. What is important, we'll see later, is that we can use these display show timestamps to kind of normalize or compare against response times. Excellent. So if I show this, actually, let's just run it and see what happens. It might be super quick because we're only showing it super quick and then closing the display straight away. Did we see that? There was a plus in the screen very briefly. One of the things it can say is from, right, let's set. So this pause command here is built into Pygaze again, and it allows you to pause and do nothing for a number of milliseconds. In this case, I set it to pause for 2000 milliseconds, which should hopefully be enough so that if we run this, we can see the screen. There's a white plus in there, and then it goes away again. Can we all see that? Yay, nay, grand, thank you. Excellent. Obviously, a fixation screen does not an experiment make, so now we actually need to do some stuff to this to make it a full experiment. There's a few things that I could demo that are potentially useful. For example, the screen class has methods for drawing images as well. It has methods for drawing other types of stimuli, just lines and whatever, if you want to construct your stimulus. But perhaps the easiest thing to do is just present a few words. So let's create a stimulus screen. There we go. All right, so the draw text function, again, is quite useful. So what I just did, by the way, in the background is I hit Command-I or Control-I on the Windows computer on this function. And what happened in the top right is that now I have the info that comes along with that function. So it tells me that what I can do to this function is I can pass the text, color, position on the screen, where the center needs to be, what the font needs to be if I have different fonts, and what the font size should be. So those are all of the arguments I could potentially use. It's nice to have that in your coding environment, because you might otherwise have like your browser open at the side to look up the documentation and stuff. So now I can just look in my editor and not have to be distracted with that. Anyway, draw text. So I can pass a text to there, say, hello. We're going to actually do slightly more advanced stuff a bit later, but for now, let's just pass a single string to there and say hello. And set the font size to something mega big, maybe 100. And instead of the fixation screen, I'm now just going to pass the stimulus screen just so that we can double check. And yes, that works perfectly. All right. So now what I might want to do is say, well, I want to actually run through a few trials, right? Because each of the each of the trials in my experiment I have in mind shows a particular word. And let's just go for words and non-words. That could be an experiment. This is going to be by no means a scientifically valid experiment, by the way. It's just going to be something that we can demo. So in my constants, I'm going to define a few stimulus words. So words is dog. And I have non-words, and those can be blorg and blorgle. Oh no, wait, we already have blorg. Blurb, how about that? Blurb, yeah, blurb is something that definitely sounds like a non-word. And I combine those two. Actually, let's find it. Excellent. So for now, let's just take the words. And one thing I could do is say words. Now we look through all the words. We create a screen specifically for that word, which so we should actually do still. Make sure that we set the word there. And then we show that screen. The one thing that I should still do actually, words is only defining the constants. I guess it's clever, but not so clever that it automatically detects that. So one thing I should do is say from constants import. I could say import words to specifically just get the words out there. What I can also do is say import asterisks, which is short for all the things, everything. It just imports all the constants I have in my constants. And then words should also be available. So now I go to my terminal and I start my experiment again, and let's see what happens. Ooh, everything really fast after one another. That's because I forgot to also indent the timer that actually showed it on the screen for a while. So let's do that again. Boom, dog. Excellent. So it's showing all the words as it should. This is great. We now actually have some sort of a semblance of a trial structure. What we don't really have yet is the non-words in there, but we'll come to that in a second. What we also don't really have in there is a response. That's quite crucial in a lot of our experiments. We deal with responses. So I'm going to build that in as well. So I'm going to say at the top of my experiment again, from pygate.keyboard. There we go. And now at the start of my experiment, I can initialize a key. And now the nice thing about this is that I can use this keyboard item. So let's call it a KB, nice and short. Is always remember the capital K on those classes. Again, this is by convention, but most class names will start with a capital and be lowercase later. Variables are all lowercase and constants are all uppercase. Convention doesn't have to be like that, but it's nice to do it in that way to kind of know what you're dealing with. After I initialize my keyboard, I can use it to obtain keyword responses. And one way I can do that is by saying keyboard.get key. There's a few things that I can do to this get key function. I'm just going to hit Command I again to retrieve it here in the top right in my editor. So I can pass a key list. I can see now, and I can pass a timeout, and I can pass something called flush. So let's do those one at a time. The key list I can pass is a list of human readable keys. So if I pass, for example, 1, that will be the 1 key on my computer. If I pass A, that will be the A key on my computer. If I pass left, that will be the left arrow key on my computer. So for now, let's pass left and right. And let's say the experiment is to click one button if you see a word and click the other button if you see a non-word. So if I hit left, that'll be my word. If I hit right, that'll be my non-word. Like the other thing that I could pass was a timeout. And essentially, when you call getKey, and if you say timeout is none, it will wait indefinitely until the participant hits a key, hits any of the allowed keys specifically. Now, that is something that you could want. For example, you might want to give people indefinite time to read through instructions at the start. But it's also something you might not always want, because you might say, well, I need a fixed response time for my stimuli. So I could also set the timeout to a particular time. Let's say I'm waiting at most 3 seconds for this Git to respond, and then I'm going to go ahead and just consider this a timeout. If that does happen, then the response you get back isn't a key that is pressed, which we'll get in a second, but it's just none. Anyway, I'll show you that in a second. The last thing you could pass is flush. And flush is a Boolean, or is expecting a Boolean. And it allows you to do essentially when you start asking for the keyboard input to forget everything that happened prior to that. So you can set this to true, and then only from the moment that my keyboard.getKey is activated, I will start listening for keyboard responses. If I set it to false, what happens is that key presses prior to when I actually called this getKey function could also be registered with this getKey. So which one of those you want kind of depends on what your aim is. Usually you will want to only look at keyword responses from a certain point in time and not prior to that, because otherwise it can seem like people responded before you actually turned on the option to respond. So usually you want to set flush to true, but there are certain cases where you don't want to do that. For example, if you're passing through this very quickly and just saying, well, I'm going to check whether somebody has already pressed the key since the last time I checked. Could be useful if you want to do this every single frame, for example. At this point, it doesn't really matter too much. I'm just going to ignore it. And then if I ignore it, it'll default. Cool. So there are also things that I can get back from my getKey. So just like display.show returned a timestamp, getKey returns a timestamp as well, plus the key that was responded to. I also noticed, because in the top right here in my editor, under the info, it tells me that. So it returns 2 things. The first one is the key that was pressed, and the second one is the time at which it was pressed, again, in milliseconds since the start of the experiment. So I can get from this key, let's call this time 2. So time 2 is when I hit the response, and key is whatever the response was. And as I said before, if you time out, this key value will be none, so nothing. Whereas if I don't time out, this key value will be the string that tells me in a human readable way what the key was that was pressed. So for example, in this case, it's going to be either left or right, because I can only press the left or the right key button. And just for my own benefit, I'm going to print key, T2 minus T1 to the console. So essentially, what I do here is I print the key, so you just get the name of the key that I pushed. I also subtract from T2 T1, so that I know how many milliseconds it took me to press the key from the moment that the display was shown on the screen. And I'm going to get rid of that pause that we had there. Actually, I'm just going to comment it out because I will get back to it. All right, so now I'm going to run this again. And I see dog, I press the left button. I see cat, I press the right button. I see fart, I press no buttons. And what we see now in our print statements all the way over here on top, I highlighted them. The first time I pressed the left button, that's right, I hit the left button. And it took me 1,284, almost 85 milliseconds to do that. The second time I hit the right button and I hit that button, it looks like in 1,426 milliseconds. And then the last time I didn't do anything. So we had a timeout, which resulted in this none for the key. And the timeout happened at 3,000 milliseconds, which is actually right because that's exactly the timeout that we set in the actual code. So that would be how to get a response, and also incidentally, how to compute a response time, because this 1284 and this 1426 is exactly my response time for hitting those keys. Are there any questions so far? Then I propose we follow the schedule for a wee bit, which is to say for the next 13 minutes until 2:30, have a little break, grab some coffee, go to the bathroom, do that kind of stuff. And then at 2:30 sharp, we start again and we continue to kind of finish this experiment. What was on the schedule is both experiment building and how to do Python in the lab. And as you hopefully appreciate, this encompasses both of those things. What we're doing is creating an experiment, which is the experimental part, and how you would use Python in the lab is exactly in this way, by running your experiment through the console. And potentially editing your experiment if you wanted to on the editor here. Likely what you'd actually be doing is editing your experiment on one computer, copying that over to your lab computer, and then on the lab computer run it on the console. Excellent. So see you in about 12 minutes. Have a coffee, a little break, and maybe. All right, it's 2:30 sharp. So let's crack on. One question before the break was, where do these variables get stored? Where do the key and the response time go to? And the answer for that is they are currently not stored, but that's the next thing that we're going to add. So obviously a crucial thing for every one of us who has done experiments in something like ePrime or any other kind of graphical user interface is you have to click, turn logging on. Or if you've ever used to buy a semi and you forgot to unpause the recording, this will be very familiar. You've run your experiment, you've wasted countless hours running hundreds of participants, and you forgot to record it. Oops, no data. So one of the main things that you want to really make sure in your experiment is that your data is here, and the tool to do that is built into Pygaze as well. One of the things you could do is use the same kind of file structure that we've seen before. So you could potentially say, with open and then whatever your file name is and la la la. You could also just leave it up to Pygaze or leave it up to whatever else environment you're using. In this particular case, we're going to say from pygaze.log file import. Log file, there we go. That's the class that we need to create a log, and we're going to initialize that here as well. So initialize the log file. There we go. I'm going to say log is log file. There we go. Now this will start off with just an empty file. The default is that it's comma separated values, and that's super useful. One thing we do want to add is we want to write a header to it. And the way that we write to these log files is by passing a list. So a list of values to be written to the log. I again did Command I or Control I on the function to pop that up in the editor here. Super. All right. So let's say I want to write a trial number. Note that whatever I write here is just my header, and I actually need to make sure that what I say I'm going to write in my file is actually something that I will write in my file. I'm completely in control of that. There's nothing automatic happening here. I might want to log the trial start. So that's the time of the first, you know what, let's call this stimulus onset. And I also want to record the response, and I want to record the RT as well, the response time. Oh, and I want to record the stimulus, of course. That makes a lot of sense, doesn't it? So stim, excellent. And maybe I also want to record the stimulus type, because that could be word or non-word. Let's make sure that they're all visible. Excellent. Okay. So after I've just written that, the only thing that's now in my log file is that header. So now I need to actually do the logging during the experiment as well. So after getting a response, I could say, log, there we go. And now, trial number, I've not actually defined yet. So I'm just going to leave that a string for now and come back to it later. Stimulus type, I haven't defined yet either. I currently just run through all the words, so I'm going to come through that later as well. Word, I did define. Stimulus onset, we also know, that's T1. The response, I know too, that's the key. And the RT, I know too, that's T2 minus T1. There we go. Excellent. So now, what should happen if I run my experiment? Left button, right button, left button. That's my lab meeting. So left button, right button, left button is what I pressed. And what should have happened is that those were now written to file. So I'm going to look in my Finder here, and I see that I now have this default.txt written there as well. I'm going to open it to see what is in there. Oh, it looks like we have trial number, stimulus type, stimulus onset, response, and RT. That's exactly what we said that it should write. Trial number, stimulus type are undefined, but the stimulus is dog, cat, fart, so that's great. That's actually logged right. Stimulus onset is logged right in milliseconds. The response is logged right in, or left. It's the key that was pressed, and the RT is also logged correctly. So that's great. Now we actually have a record of this. The downside is that this is called default.txt, which is a bit annoying. And every single time that you now run an extra participant, it just overwrites the default. And the reason it's done so is that we didn't actually set a path for this log file to be at. All right, so let's shape some order in here as well. So visual stuff. Just going to put that all together. This is stimulus stuff. And here we have files. Okay, just going to import the OS library. That's one of the things that we looked at yesterday, because it has the os.path stuff. Now I can locate my directory by getting directory name of __file __. It was one of those things that we saw yesterday very briefly that don't really work very well on Jupyter notebooks, so that will work really well on a computer. __file ___ makes the path to the file that I'm currently running. If I ask for the directory name of that using the OS path module, what I can get is the path to the directory that this file is in. So this will essentially be the folder that has both the experiment files. Now what I can say next is the data directory that I want to make is path.join. So join was that way of combining two things without having to worry about what the file separator was. So I can say dir, and also I want to add to that data. Mind you, this directory does not exist yet, which is a bit annoying. So one of the things that we can do is we can create it manually by hand. So go into the File Explorer and say, create new directory, name the directory data, that's sorted. The other thing we could do is use the OS module to check whether the directory exists yet. So if is dir is for is directory, there. So we can do something if it exists, or more importantly, we can do something if it doesn't exist. So if this does not yet exist, what we can do is say os.make there, which stands for mkdir, which stands for make there, make that data directory. So essentially what we're doing here is saying I'm automatically detecting where I currently am. I'm then creating this folder the subfolder data within the directory that I currently am in. And then I'm going to check if it exists. If it exists, that's good. If it doesn't exist, I'm going to make it. So just as a little check, here I have nothing other than the experiment files in this weird PyCache folder and the default.txt in my directory. But if I run this particular file, I should see that I now have this data folder in there as well. Oh. So essentially what happened here is that I created it purely through code. If I run this again, I'm just running it within the Spider environment now. Nothing should happen because now it was already made, and you can also see that it's still there. It's still the same thing. So now we have a data directory, and now we can say, well, I want my log file name to be something that's specific to the participant. So I'm going to come back to this name. I'm going to come back to that. For now, give it a placeholder, say subject 19. And then I'm going to say log file, all caps, is os.path.join. We're going to join the data directory and the log file name. And this is where the exciting stuff happens. Log file name as well as log file are both things that Pygaze automatically recognizes and will use to store the log file that you make. So log file will be automatically picked up, including all the paths to it, to the directory. And then it will be using that when you say, create this new log file instance, which is quite useful because, again, I can just set it here and then I don't have to worry about what happens in the script. I can just change it if I wanted to here. So now what happens if I run my experiment? Where's my map? I'm going to hit the right button, the left button. I'm going to wait and just not hit any buttons at all. Boom. Then I'm going to check the folder that my experiment is in. And now in the data directory, we see that we have a new subject, subject 19. And if we open that subject, it has the right, left, and no key press that I just made. So that's great. It actually saved it to the right space. So now the only thing that we still might want to do is actually change that subject name, because if I have to change it manually every single participant, it's a pretty big chance I'm going to forget at some point to do that and then overwrite somebody else's participant file. So I don't want to do that. So instead, I'm going to use this little trick, which is input. Now, input is a excuse me, is a function that asks on the terminal. So whenever you're running it in the terminal, it'll ask you a question that you can set yourself. So, for example, what is the participant code? Boop. Excellent. So now it'll present that specific question in the terminal. And what it allows you to do is type something in there and then hit enter. And then it'll use that in the actual program. So it basically you're self-defining whatever the string is on the log file. Now, if you're still using Python 2, because of whatever reasons, you can say raw underscore input. It's the same thing. Just that raw input doesn't exist anymore in Python 3. So here we use it like this. So now if I run my experiment, the first thing I get is, what is the participant code? I say, I guess PP19, maybe I use that thing, or I can maybe say healthy control underscore 019. Let's make it nice and professional. Run through the experiment again, left, right, left. And now in my Finder, I can see that I have HC underscore 019, and in that file, I have the exact behavior I just pressed on my buttons. So that's great. That's how you store data to your from your experiment to your actual machine. The nice thing about using as log file structure is that you don't really have to worry about the intricacies of saving data and writing to disk and flushing the RAM, etc. That's all handled by the log file, so you don't have to worry about it. Brilliant. So next step. One thing I want to do is make sure that I start my trial with a fixation screen. I didn't create it for nothing. So I'm going to do that as well. Screen. And then I'm going to use that timer function I had before to wait for a wee bit before then. So this will tell the participant that the stimulus is coming up. Let's just wait for 1 second. Let's not make it too long. This is next up. Response. Excellent. So now we are in a place where we already have a bit of a trial. What we probably also want to do is clear the display afterwards. So after you put a response, we say, if you say this.fill, it essentially just fills with nothing. And then this.show, and then pause for say 500 milliseconds or something. So there's a wee bit of time between the trials. Normally you want to jitter these times a bit, especially in the scanner, you want to jitter these times a bit, but we're not going to deal with it right now because you can just use the random interval function that we learned about before to use that. So one thing we still want to do is create a proper trial structure, because right now we're just rushing through all the words. It's not really that elegant. And also we're forgetting to put the non-words in there. It's also the same order every single time we run this. So we want to make this a bit more elegant. We want to create a trial structure. And for that, I'm going to use one of those data structures that I've shown you yesterday. So create a trial structure. And that's the dictionary. So I'm going to say all trials is a empty list for now. And what I'm going to do is I'm going to essentially add to this a trial for each of the words I have and for each of the non-words that I have. And what I'll be doing is for each of those trials, I'm going to create a new dictionary. So I'm just going to, before we even start creating the actual trial structure, do a little kind of small, just little test so that we can see how this works in practice. So a single trial will be an empty dictionary. And then to that, we can add the stimulus type. So for example, that can be word. We can add to that the, so let's say cat, for example. We'll fill this out a bit later. And, and that really is all we need right now. So then what we need to do is say all underscore trials. That's that list of all trials dot append. We want to add to that list the new trial that we made, which was this nice, the new trial that we made. And instead of running through all of the words, what we want to do is for trial number, comma, trial in trials. Excellent. So trial number now is updated on every single go. It's just as if you would use I, for example. You can give those iterators every single variable name that you want. I just usually go with I, J, K, and so on, which is, again, kind of convention. It's nice. The trial number is much more informative, so we use that one now. And trial is just whatever the next dictionary in that all trials list is, which for now is just this one trial, and we're going to come back to that in a second. So now what we want to do is actually pull out of that the word. So where previously we just used word, instead now what we want to do is say trial stimulus, because we have to find it in the trial dict, so we can just refer to it now here. There's one other place where we refer to word, which is here when we log the response. So we kind of want to update that as well. The neat thing is now that we also have the stimulus type, we can refer to that within the trial as well, because it was nicely tucked away here too. And the trial number, we now also define. That's the trial number over here. So we can also stop making that into a quote. There we go. So I'm just going to run this, and I'm going to run it with that single trial just to check whether everything works. Then after that, we're going to come back to actually creating the trial structure. Oh no, what happened there? I'm frankly not entirely sure what happened there. Let's see what was logged. There it was cat, stimulus onset, what happened? And I clearly didn't wait for a thing. Oh, I see what happened there. Okay, so what I forgot is to make sure that the display was shown here, because I copied that over, or at least forgot to copy that over. Let's call this T0 when the fixation screen comes online, and then call this.show here. So essentially what was happening now is that in the background, we created our trial stimulus screen, And then what didn't happen is that we actually put it to the front, so we couldn't actually see it. So let's try that again, because that we clearly cocked up. There we go. Fixation cross, stimulus, I press left. There we go. Okay. So what's logged to the data now is my trial number, correct, my stimulus type, that was a word, my stim cat, my stimulus onset, and my response time. Excellent. That's everything we needed right now. So now we can go back to creating this trial structure. So the first thing we want to do is we want to loop through all of the actual words that we have. Add all words to, so for word in words, so for each of those new words, we want to create a new trial empty dictionary. We want to say the stimulus type in this case is word. And now we want to say that the stimulus is that word that we are currently looping through. And we want to do the very same thing. Oh, and we want to then append that trial to all of the trials. And we want to do the very same thing for all of the non-words. So looping through all of the non-words, this time I'm going to set that stimulus type to non-word and add that still using the same variable name. Doesn't really much. There we go. Excellent. So now at the end of this, my all trials list should contain many, many more words. And what I want to do now is just running through all of those. Press the left button, press the left button, press the left button. These are all words. Right button for a non-word, right button for a non-word, and right button for a non-word. Excellent. Okay, let's check that file. Excellent. Everything came through all right. So that's brilliant. The annoying thing, all of these are completely deterministic. So none of this is randomized. So one final thing that I'll be doing now is importing the random module. And this is a module that's just built into basic Python. Yesterday, we've seen a numpy.random module. It's very similar to that. One of the things we can do with the random module is shuffle a list. So we can say all randomize the trial list. We can say random.shuffle all underscore trials. And so what we're not doing is saying all trials equals random.shuffle, because random.shuffle, as you can see here, shuffles in place. So the moment that we call this, that all trials thing is already shuffled. It's kind of a confusing way, I guess, if you're not used to the in place bit, but that's essentially how it happens. So you don't even have to say all trials equals shuffle. It's just already done for you. So we now have a very brief experiment that just runs through a bunch of randomized words and non-words and allows me to hit the key for each of the words and non-words that I might have, which is, as I said at the beginning, it's not a good experiment, but it definitely is a experiment. And I'm going to leave a wee bit of a gap now to ask whether anyone has any questions that they might like to ask at this point. Okay. Again, if you do develop questions, just shout. The next thing that we can do is give a little bit of feedback. So one other thing that we can do is within PyGuess is a sound as well, and you can use that sound to create beeps and boops and really quite annoying sounds as well. And so one thing you could do is whenever somebody presses a button and it's the correct button, give them a nice little feedback sound. If it's the wrong button, give them the wrong feedback sound. And I say from pygaze.sound, so where I need to be, import sound. Now you might see me, by the way, just order these imports in a particular way. This is completely random. It doesn't really, the order in which you import them doesn't really matter. What I usually go for is basic imports first, then whatever small cute little library I'm dealing with, and then my own predefined imports I self-define here. But it really doesn't matter. You can just pop anything in there. What I would stick to is importing on the top of the script, but other than that, there's not really any rule. So I'm going to initialize two sounds. The first one is the good sound. And so I'm going to say good sound is sound. Oh, actually, I can just that here. There's a few things that I can pass through my sound. So one of them is the oscillator, and the oscillator for a nice, slightly nice sound is always a sine wave. That's just a really pleasant thing of looking at, of listening to. It's not always that, but this is one of the prime things you could potentially use. One thing you could also set is the frequency, and let's set this one at 440. That'd be great. Or in the length we can set as well. I think it's a length keyword, but might also be sound then. Don't know if I heard. Let's see about that. You know what? I'm just going to use both of them and see whichever one is right. You can look this up at home later. All right, so I'm going to make a roughly similar sound, but then this one is going to be a bad sound. And one really jarring way of presenting sound is in a square wave. You can also set it to a saw wave. A square wave is like step up, step down, step up, step down. A sawtooth is saw up and then directly down, and then thing up. In fact, let's just set it to saw. There we go. One thing that I don't think you'll get is the actual sounds that play, because they're played over my headphones and therefore don't actually show up on the Zoom. But I'll try to make a response that's somewhat coherent with the actual sound that's going on. Excellent. So now the only thing we need to do to actually present that feedback is to check which of the two we should present. So we can do this after we log this response, for example. We can also do it before then, doesn't really matter. But the bottom line is we need to check the response. So basically, if the trial stim type equals word, and the other thing that we need to do is check whether the key equals left. So that's one of the correct responses, left or word. The other correct response is the non-word and the right button. So actually, let's just set this as a different thing. So right is either this. We're going to encapsulate those in brackets and say or with that or thing. You can also use the word or if you prefer. And the other stimulus type could be non-word and right key. And now we're going to say if good sound dot play, else bad sound. There we go. I mucked something up in the something going wrong somewhere, and I think it's this, but it's not. Let me just deconstruct this. This will be all right. Brackets are fine. These are fine. These are fine. For the life of me, I can't figure out why. Spell something elsewhere. Maybe look at. Okay, well, me. It's flagged as correct now. Anyway, the logic here is if the stimulus type is the word and also the keys on the left, that's the correct response. However, the other option, if the stimulus type is non-word and the keys on the right, that's also a correct response. So either of those is correct, anything else is wrong. So now if we run the experiment, we get either the good sound being played in feedback or the bad sound being played in feedback. And that sounds either really nice, like a sine wave, or really grating, like a square wave. Just going to run that. Just going to go to say, again, healthy control, 019. Sound line was the wrong one. Excellent. So stimulus, I hit the left. Oh, I get a nice pleasant sound wave. I hit the left. Ow, that was really, really bad. Okay, so try that at home and see how jarring exactly that square wave is. The sine wave is much more pleasant. It's like a boop. Right, let's check whether the data file is actually correct. Looks fine. Response times seem all right. Responses seem all right. Words and non-words come through. So this is the basic standard kind of way of potentially doing an experiment. There's one additional thing I will show you here, but even I can't run at this particular time because I don't have an eye tracker attached. But one of the really nice things about this particular library is it's really easy to connect the eye tracker in there as well. So what I can say is, mygaze.eyetracker import eyetracker. And then I need to initialize that, which I will do here. So there's a few things you need to do in an eye tracker. The first one is the calibration sequence, and you normally run that all the way to the start of your experiment. This is where the actual experiment starts, all the way here. Normally, actually, this is where you would first put in a instruction screen so the participant knows what the hell is going on. But for now, ignoring that for a wee bit, you do that in the same way, right? With the stimulus screen, or the screen, and then passing that screen to the display. So now we're going to say calibrate the eye tracker. And that's actually really easy. You just call tracker, not calibrate, and then boom, you have a calibrate eye tracker. Normally, what you also say for each of these trials is that at the start of the trial, you want to have you want to record whatever the eyes are doing on the screen, where the gaze is going. So this is the kind of the preparation phase where we just draw things on the screen, and only after that we set this fixation screen on. So this is roughly where the trial actually starts in earnest. So here we can say start recording gaze tracker dot start recording. There we go. One other important thing is to make sure that in your data file from the eye tracker, you know what's going on as well. So I can say tracker.log. And one of the things I might want to log in here is actually what's happening during the trial. So I could say stim type is, fill that out, comma, stim is, I'll fill that out too, and trial number is there. Let's not use commas, but so we got formats. Trial number. Let's get all of these on the same page. There we go. And trial type. That was my dictionary key. Another trial stim. Excellent. So now I have my data both in the behavioral data file where I log all my keyword responses, but I also have it in the eye tracker file. It can't hurt to double code these things. Another thing that's important to trackers is to make sure that you have a timestamp in the log file whenever you do something. So whenever the screen changes, essentially. So I'm going to make a log message when the fixation screen comes on. So let's say fix onset. I also want to have that log message when the stimulus comes up. So, and I want to maybe have that when the response is being made. And then I guess I could potentially also put it down here when the sound is being played. Know that whether or not you get the onset of the sound correct is a bit different. So for the show method, what will actually happen in the background is that your program is waiting until the start of the vertical refresh. And therefore, basically, it gets you the exact timestamp of when the onset of the screen was, provided all your settings are correct. Whereas if you start playback for a sound, you're just passing something onto the sound card and they're just hoping that things are all going to go all right. So this doesn't actually block until the actual onset of the sound. So therefore, the sound onset logging might be ever so slightly off, depending on what your system is. And there might also be a like random error on that as well, which is why it's really important if you work with sound to have a good sound card, and also B, measure what your system does in order to get these logs right. Because there might be, if there's a no or very little random error on there, but a very systematic error, you could just wait for that systematic error, let's say 50 milliseconds or 500, and then you're sure that your onset is logged correctly. Really important if you work with sounds, not super important otherwise. And then at the end of the trial, we want to stop recording, which is actually pause recording to the eye tracker. Okay, so that the tracker.stop recording. There we go. And then finally, all the way to the end of the experiment, we want to close the eye tracker connection as well. So there we go. Excellent. Now, there's two ways in which we can actually tell the tell Pygaze what eye tracker we're using. The first one would be to go here and say tracker type is, and then whatever your tracker type is. The better way, I would say, is to define it again in the constants, where you could say, and say tracker type is ilink, for example. Or iDrive also support for that, or SMI also support for that, or Toby also support for that, or gaze points, or actually open gaze, which is the API for gaze point, or Alea is also a new one that we support. Anyway, ilink is the one that we have at the CPU, so I'll use for set that one. If you want to try it at home and not in the lab, and you don't have an ilink on you, then you can set the dummy mode to true, and then whenever you run your experiment, you don't actually connect to the eye tracker, but you just pretend that you do, and then the mouse kind of gets used as a stand-in for a game. So essentially, this is how you create the basics of an experiment. If you do imaging, I won't go over it now, but we have a library for specifically the CBU as well, where you can send triggers or to the MEG data file, for example, or where you can wait for the MRI scanner for its sync signal to come in, or button presses that people do in the MEG or the MRI scanners. We also have a thing that helps that. It's the scan sync library, and we have that on the GitHub page for the CBU. And both Johan and myself would be very welcome to help you with that if you have an interest in creating experiments in Python and want to integrate that. I'm going to leave it out of this example here today because it's very specific to the CBU, and also I'm not entirely sure how relevant it is in the current situation to know exactly how to do a scanning experiment. So with that, thanks for your attention here. I'm going to leave my screen share open for now because maybe there's any questions. Are there? Yay, nay? Doesn't seem like it, so I'll stop sharing and my screen is safe again. Excellent. I am out of how can you load external stimuli? That's a really good question. So let's, in the background, create a new folder, call that folder images. I'm just preparing something whilst I speak, so I might be talking absolute nonsense while I do it. And I'm also trying to find a image on my computer in the background as well. I have a few of these funky stimuli that we can use as a nice example, but I do have to locate them. So bear with me. Yes, found it. Sample experiment. Boom. All right, so popping screen sharing back on, boop, and boop. So the question was, I just realized that in the recording, we don't actually record the questions, is how can I load external stimuli? So for that, I created this external stimulus right here. I made a folder called images. I like this kind of folder structure because then you just have your constants, your experiment, and whatever other Python files in your main folder, and your data in a different folder, and your images or other stimulus material in a different folder as well. You could also chuck them in a different place on your computer if you wanted to. I just like to have them all in kind of nested subfolders. This is our actual stimulus. It's a happy cat emoji, which makes absolutely no sense in the context of many experiments, but it is a nice example PNG to just load. So we're going to go with that. So that's the first thing that we'll do. So there's two things we need to do to actually do that. The first one is to let Python know where the image is, and the other one is to actually draw the image using the screen. So the first one would be to make sure that we have the image directory clear. So that's os.path.join dir, images, I think I called it. And then one really neat way of, let's do it here actually. So there we go. One thing we could do is say stimuli is just an empty, it's just a list, and then say stimuli, and then what was the name of that? Cat's happy emoticon. I'm going to do that for now and then come back to this in a second, because for now it's just important that we have one name in there. So I'm muting myself. Sorry, that was my bad. I got another Zoom call, hit the wrong button. We're going to try and grab the stimuli. And then from those stimuli, we're going to see if we can actually put them on the screen. So for that, I'm going to create another screen over here. Screen. I'm just going to say im screen is screen. Again, it doesn't really matter what you call these, and the screen automatically gets the right resolution info from the constants. I'm going to say im screen dot draw images. I think we need. So there's obviously the image that you actually need. So in this case, that is stimuli 0, because the first image that I put in the list over there. Which is now the full path to the image drawing stimuli. Now it's the full path to the image file. So essentially, we're stringing together the image directory and then the name of the stimulus. So now stimuli 0 is the first position in that stimulus list, and it's just a full path to that stimulus. There's a few things we can do here. So for example, the position we can define as a position in pixels. So we can set that to 0, 0, for example. That would be the bottom left. We can also set that to 1440, 900 on my computer, which is the top right. But it would make more sense to go for half. So one thing we could do is say 720 and 450, because on my computer that works as half the stimulus position. I could also actually manually compute that. So image position, for example, I could say is this size divided by 2, 0 divided by 2, this size 1 divided by 2. This would be the middle of the screen. You can really do anything you want using the position argument, as long as you make sure the positions are in pixels in your screen, with 0, 0 being the bottom left and whatever the maximum values are on both being top right. So define that here as the middle. I could potentially, if I wanted to, scale this up. So I could say scale it to 2 times as big, or scale it to half as big as it was before. I'm not going to do that now. I just wanted to present it in the center in its own original size, but you could do that if you wanted to. And then I'm going to say fill my image screen, and I'm going to say this book show, and then I'm going to say get key. Okay, so this is a bit hacky, because what I'm just doing is showing that screen on the display, and I'm just waiting for whatever key to start at the start of my actual experiment. This makes very little sense, but it's a nice demo for just showing how you do those stimuli. So if all goes well, we should now see a black screen with a cat in the... Oh, sorry. Eye tracker takes the display as an argument. You pass your display to your eye tracker because it does some drawing during the calibration, so it needs to know what you're displaying. It doesn't really matter for the image, but it does matter for the start and the back. And voila, there we have our wonderful cat in the background. So that's how you can draw a external stimulus on there. One thing you could also do, for example, is create multiple. So this draw image, you can just call that however many times you want. So I could create however many cats I want to on the screen, or other types of stimuli. Most image files, image formats are supported. So in this case, it's PNG, JPEGs and stuff, also all fine. So that's a neat way of drawing in an external stimulus. As I said, this is a bit crummy, perhaps. So one thing you could also do is automatically detect what the stimuli are in your image directory, which you could do in this way. So you say stimulus names is os.list there, which is a command that gives you all of the files within a directory. And then you could say for stimulus, for stim name names. We saw that yesterday. It's essentially the way to say, I want to split the name, let's say cat, and the file extension, let's say PNG. And if the extension is what you expect it to be, then add that stimulus to the list of stimuli. And instead of actually drawing in the full name, you just say stim underscore name. So one reason for doing it is that sometimes there might be other files in your image directory as well that you accidentally put in there, and you don't want to accidentally draw those as an image. So it's good to check for the extension. So essentially what you're doing here is automatically detecting all of the images in your directory with the images. You're looping through all of them, and you're adding to this previously empty list whatever your stimulus is. And then you can use this stimulus list in very much the same way as we've used words and non-words previously. Loop through there, add the stimulus to your trial list, and then do whatever you want with it during your trial process. There's one more question in the chat, which is how do you abort the experiment? You saw me do that just now, and it was essentially on Mac, it is Command and then Tab. So essentially what you need to remember is that in the background, there's always the terminal still open, and this full screen is just running at the front. So if you say Command Tab, what happens is that you're highlighting whatever the next thing is. So that would be the terminal in my case. And then you say on Apple Command and then a full stop, and it just kills it. On Linux and on Windows, you would say Alt Tab and then Control C for killing the experiment. So what happens there is you essentially highlight in the background the terminal and then say either Command full stop or Control C to kill the experiment. The other thing you can do is just hit Control Alt Delete on Windows, for example, and then select the Python process and say kill. That also works. I prefer the Alt Tab method because if something weird happens in the background, then you should still see that. Another thing that was already automatically built in, whenever you run into a Python exception, so an error, the experiment window should also close down, provided you run it from the terminal. So that's already sorted. Another thing you could build in is, I'm going to share the screen again to just show how to do that. One of the things you could potentially think about doing is in your keyword response or somewhere else in your trial logic, also build in, for example, escape, and then say if key equals escape, close, and this will close. So this is a way that you can actually couple the keyboard input to escaping your experiment as well. You could also manually do something like raise exception. So this is an error, and then escape rest. This is how you make your own error messages. So raise exception just pulls a Python error, and then whatever you pass here as the string is the reason for the error that's shown in the console. So that can be a really neat thing to do as well, and that exception already kills the experiment. Otherwise, make sure that you close the tracker in a nice order and make sure that you close the display in a neat order if you do want to kind of manually build in one of those escape options. Also remember that if you can do this, your experiment participant can do this. So you might want to make this contingent on a dummy mode, for example, that you can set in the console. So yeah, if your experiment crashes and if you run it through the terminal, you should already kind of have it automatically closed down. If you want to prematurely kill it, you can either build a premature kill inside of your experiment by doing something like this, or you can press Alt-Tab and then Control C if you're in Windows or in Linux, or you can say Command-Tab and then Command full stop to kill the process if you're on Mac. Any outstanding questions? We have about 4 minutes left. Yes, Charlotte, it's a really good question. So what you're asking is if you could use auditory stimuli as well as visual stimuli. So that that sound that I showed, and I set the oscillator to something and then the frequency to something. That's a way to make your own sounds within the actual experiment. The other thing you can say is when you open that sound is you can pass a file name and say sound file equals and then the path to your file, and then it automatically loads the sound from that file. And that only works if the file is in uncompressed WAV, so a WAV file, or an OGG file, which sounds really gangster, but is really just an open source file format. And the idea is that you can actually then also just load whatever your sound is that you have stored on file. So that's one way to do that, and it would work in the same way as the other sound. So whenever you say, so if you create your sound saying my sound equals sound, and then sound file is whatever the path of your sound stimulus is, and if you say sound.play, it'll play that sound during the experiment. So I often use that for playing ka-ching sounds during reward tasks, for example. It's a really neat and efficient way of just pulling in something extra. Your other question is really, really good, whether you can use the delay time. It really depends. So not with any of the functions that we have here. One thing you could do is log the time that you send the request for the sound, and then externally with a microphone log when the sound was actually played. And then the time in between those, just run that over and over again. So you can log the timestamp of the, sending your sound play request to the sound card, and then the headphones or the speakers that you're using actually producing the sound. If you run that over and over again, and if you have that timestamp logged by an external microphone, you should be able to get a nice distribution of what the delay times are. That's the best way of getting at this, because that will be different between all of the different setups that you might use, and whatever their sound card or their other specs are. So there's unfortunately not quite as an easy programmatic way of getting at that as you would have in the visual like frame onset sphere. So you'll have to grab an external mic and just run your own tests, unfortunately, which arguably you should be doing with your visual stimuli as well. Strap a photodiode to the screen to check the actual real delay times. But there's a programmatic way of doing it. So people often pass by that point and assume that their onset times are correct, which is arguably not the most safe thing to do. So if you are dependent on super precise presentation of visual or auditory stimuli, you really ought to test it with either a photodiode or a microphone. Good question. Excellent. And then we're at 1/2 past. So I think that's the end. We made it.